Night falls on the ancient world. Above, countless stars pierce the darkness, a vast sparkling tapestry that has captivated human eyes for as long as we have existed. In the hush of primordial nights, far from any modern glow, the sky was a theatre of mystery and wonder. Our earliest ancestors looked upward and saw gods and animals, heroes and monsters, all outlined by patterns of stars. By the flicker of campfires, they whispered stories about those lights, tales explaining how the world came to be, or how the spirits in the sky watched over them. Under ancient skies, imagination and observation merged. The glittering band of the Milky Way overhead might be seen as the river of souls, or the pathway of gods across the heavens. Constellations, the groups of stars that form familiar shapes, became characters in cultural myths. One society saw a great hunter with a mighty belt and sword striding across the sky. Another saw in those same stars a giant bear forever turning around the North Star. In the southern hemisphere, people connected different dots and traced out their own cosmic creatures. With no telescopes or scientific instruments, early people wove what they knew into celestial lore. Each sunrise, each moonrise, each comet that blazed unexpectedly was imbued with meaning and magic. Yet these early sky watchers did more than spin tales. Over generations, they noticed patterns in the lights above. The stars moved in fixed arrangements, night after night, and year after year, while a few bright points, the wandering stars, roamed their own curious paths. The sky was not random. It had a rhythm and a reliable order. By careful observation, ancient astronomers began to discern that rhythm. Millennia ago, priest astronomers in Mesopotamia meticulously recorded the positions of planets and the timings of eclipses on clay tablets. In those records lay the knowledge to predict the return of the seasons and even rare events that once seemed capricious. In the fertile lands of the Nile, Egyptian sky watchers learned that each year, just before the annual floods, a certain star would reappear at dawn after months of absence. It was the star we call Sirius, and its rising heralded the life-giving inundation of the river. Across the ocean in Central America, Maya astronomers observed the skies from temple-top observatories. They too tracked the cycles of Venus and the Moon, even predicting eclipses within their calendar codices. Astronomy became a tool of survival and planning as much as a source of wonder. Picture a clear night in ancient China. Royal astronomers stand on a tall tower, eyes trained on the brilliant moon and the array of stars. The emperor depends on them to interpret heavenly signs. A sudden darkening of the sun in daytime, a solar eclipse, could strike fear into millions. To many, it seemed that a great dragon was devouring the sun. People would shout and clang gongs to scare the dragon away. In truth, some learned sky watchers had begun to grasp the patterns behind eclipses. By around 600 BCE, Babylonian scholars had identified cycles that allowed them to anticipate when the sun or moon would go dark. They could not prevent these celestial events, but knowing when they would happen turned terror into awe. And indeed, being able to foretell an eclipse lent great power and mystery to those who understood the sky. For ancient civilizations, the sky was not just a calendar, but a cosmic omen. They believed the heavens mirrored events on earth, the birth of a king, the fall of a city, the fortune of a harvest. All could be written in the positions of the planets and stars. Astrology and astronomy were twins in those days. By understanding the patterns of the sky, one might divine fate and gain favour with the gods. Kings and emperors employed learned astrologer priests to watch the heavens and interpret what a bright comet or a rare alignment of planets might mean for their reign. An unusual celestial event could be taken as a warning or a blessing. In this way, studying the sky was as much about finding meaning for human lives as it was about the cosmos itself. Across cultures, the sky became a grand clock and compass. The moon's gentle phases counted the passing of time. Indeed, the very word month grew from moon. The sun's yearly journey across the backdrop of stars marked planting and harvest seasons, the coming of winter and spring. At particular times of year, the sun rose or set at special points on the horizon, and ancient peoples aligned their monuments to these moments. On Salisbury Plain in England, massive stones were arranged so that on midsummer dawn, the first rays of sunlight would dramatically pierce the heart of the circle at Stonehenge. Far to the north, in a green Irish valley, a Neolithic tomb at Newgrange was constructed with a narrow passageway that fills with sunlight at the exact moment of sunrise on the winter solstice, lighting up a dark chamber that waits in blackness all year for that single day. On the other side of the world, Maya pyramid temples were designed so that on equinox days, the sunlight and shadow would create the wriggling shape of a serpent along the stairs, as if a god had come to visit. Such feats required careful watching of the skies and precise record-keeping. Generation after generation refined this knowledge, passing it down as sacred wisdom. Under the stars, navigation was possible too. Long before compasses or GPS, Polynesian voyagers navigated the open ocean by reading the night sky like a map. They knew which stars rose and set in what patterns, memorizing their paths across the heavens, guided by the steady glow of the North Star high in the northern sky, or by the seasonal appearance of certain star clusters. Seafarers could find their way to faraway islands, trusting the heavens when there were no landmarks but the waves and wind. In the desert sands of Arabia, traders traversing long caravan routes at night fixed their course by the stars as well. The sky was a trusted guide that stretched over every land and sea. Even in everyday life, the sky served as a timekeeper and source of guidance. By noting where along the horizon the sun rose or set each day, anyone could sense the approach of summer or winter. The first thin crescent moon after the new moon signalled a new month in many calendars, setting the dates for gatherings and feasts. The heavens were intimately linked with the rhythms of human life, from the ebb and flow of tides to the schedule of sowing and reaping. As much as myth and ritual dominated early understanding, sparks of scientific insight gleamed among the stories. Thousands of years ago, observers began to suspect that the Earth itself might be a sphere. They noticed during lunar eclipses, the moments when our planet's shadow falls on the moon, that the shadow's edge was always round, no matter the direction or time. Only a spherical Earth could cast a consistently circular shadow. They also saw how ships sailing into the distance gradually vanished hull first, then mast, as if descending behind a curve, evidence that the surface of the ocean was curved. Such observations nudged them toward a revolutionary idea. Our world was not a flat expanse, but curved like a ball. By the time of the ancient Greeks, critical thinking about the cosmos took root alongside mythology. Philosophers and early scientists in Greece looked up and sought logical explanations for what they saw. Around 250 BCE, Eratosthenes, a scholar in the city of Alexandria, performed a clever experiment. He compared the length of shadows at noon in two cities, hundreds of miles apart, on the same day of the year. By measuring the difference, he deduced that Earth was indeed round, and even calculated its circumference with impressive accuracy, using only the sun, a stick, and geometry. It was a triumph of human curiosity and reasoning beneath the ancient sky. The Greeks and other cultures even built models of the cosmos to better understand it. One remarkable relic found at the bottom of the sea, the Antikythera mechanism, is a testament to their ingenuity. This intricate bronze device, dating to around the 2nd century BCE, contained interlocking gears that could predict the cycles of the moon and perhaps the motions of planets, acting as a mechanical computer for the heavens. Long before modern machines, our ancestors were already striving to decode the sky's movements in systematic ways. Yet, in those times, science and myth were not separate domains, but intertwined threads of the same tapestry. The same Greek civilization that produced rational explanations also imagined the sun as the god Helios, steering a golden chariot across the sky each day. Most ancient scholars agreed that the earth lay unmoving at the center of everything. It felt obvious. The ground beneath did not feel like it was hurtling through space, while the sun, moon, and stars all rose and set in orderly fashion around us. Thus, they conceived of a cosmos with Earth at its heart. The heavens, they thought, might be a series of crystal spheres, one nested inside the other, turning like the wheels of some enormous celestial machine. Each wandering star, Mercury, Venus, Mars, Jupiter, and Saturn, had its own sphere encircling the world. Beyond the last planet's realm lay the great outer shell on which all the fixed stars were attached, like glittering jewels on a cosmic globe. In this elegant vision, the Earth was the central stage of creation, and all the lights in the sky were there to circle us. Still, not everyone was content with the traditional answers. Ancient sky watchers noticed subtle oddities in the dance of the heavens. Occasionally, a new star would flare into existence where none had been seen before, lingering for weeks or months, and then fading away. A mystery that defied the idea of an unchanging sky. Comets with luminous tails would streak across the night, arriving without warning from the blackness of space, often interpreted as messengers of momentous events or omens from the gods. And those 5 wandering planets did not move in simple, perfect circles as one might expect. At times, a planet like Mars would slow down, halt, and even drift backward against the starry background for a while, before resuming its forward course. These puzzling loops in the planet's paths, called retrograde motions, were carefully recorded by Babylonian and Greek astronomers. To account for them, while keeping Earth firmly at the center, scholars imagined the planets moving on circles upon circles, epicycles within their spheres. The model grew ever more complex, a testament to both human ingenuity and the deep desire to preserve the familiar geocentric idea. Imagine the curiosity and awe such phenomena must have sparked. In 585 BCE, during a battle in what is now Turkey, day suddenly turned to night as the sun vanished in an eclipse. Soldiers dropped their weapons, trembling at this midday darkness. According to ancient historians, the philosopher Thales of Miletus had predicted that very eclipse. When the sky darkened exactly as he foretold, the warring armies saw it as a powerful sign and promptly laid down their arms, ending the conflict. Whether through knowledge passed down or sheer luck, this event was an early glimpse of the predictive power of astronomy, a power that must have seemed like magic or divine prophecy. Beneath ancient skies, humanity's understanding of the cosmos was slowly unfolding. From the myths of creation painted across the stars to the first measured steps towards scientific knowledge, people were learning to read the sky. Each night, the universe offered a silent show, and our ancestors watched intently, sometimes fearful, often reverent, and always filled with wonder as they sought their place amid the vastness. In those twinkling lights above, they found stories to live by and clues to the nature of reality. The stage was set. Over countless generations, the stars had guided us, inspired us, and challenged us to understand. They would continue to do so as our journey of cosmic discovery moved forward. Night after night, one celestial companion has remained especially familiar to us: the moon. Its soft glow bathes the land in silver, turning dark nights into moonlit ones where shadows dance gently. Since time immemorial, humans have gazed up at the moon's changing face with awe and curiosity. It is the largest light in the night sky, cycling from slender crescent to full brilliance and back again over the course of about a month. In those cyclical changes, people long ago sensed a kind of living rhythm. They saw the moon as a heavenly being that was born, grew, aged, and died, only to be reborn anew each cycle. This ever-changing, yet eternal presence inspired countless legends and beliefs. In many ancient myths, the moon was personified as a deity. To the Greeks, she was Selene, the moon goddess who rode across the sky in a silver chariot, or Artemis, the huntress moving silently through the night with her bow. The Romans called her Luna, shining with a gentle light. In Chinese lore, they spoke of Chang'e, a beautiful woman who flew to the moon and lives there forever, accompanied by a jade rabbit under a cassia tree. In these stories, the moon was a place of enchantment, either a goddess herself or a distant world where magical creatures dwelt. Some cultures imagined a man in the moon instead, a lonely figure banished to the lunar sphere, his face forever visible to us from afar. Others saw animals in the lunar markings, a rabbit, a toad, or a buffalo. The glowing orb in the sky became a mirror for our imaginations. Because the moon governs the night's light, people associated it with the subtle, the mysterious, and the emotional. They noticed how the full moon seemed to influence human behavior. More feasts and dances would occur under the bright full moons. But also, it was said, more strange or frenzied behavior. The term lunacy was born from Luna, reflecting an old belief that the moon could drive people to madness or transformation. Folklore across Europe told of werewolves whose curse was triggered by the full moon's light. Whether or not the moon truly affects our minds, its presence has certainly affected our hearts and stories. The moon also became a universal timekeeper. Its phases were the basis for the first calendars. Each new moon marked the start of a new month in many ancient societies. People would watch for that first thin crescent in the twilight sky, knowing that a new cycle of time had begun. Entire festivals and rituals were timed to the lunar cycle: planting and harvest festivals, tides of fishing, religious fasts and feasts like the full moon gatherings in cultures around the world. 12 full moons roughly marked a year. And even today, many calendars and cultural events remain tied to the phases of our moon. At times, the moon gave the night not just light, but drama. Imagine an ancient night when a full moon suddenly begins to darken, a bite seemingly taken from its glowing disk. A lunar eclipse is underway. The moon slowly cloaks itself in Earth's shadow, sometimes turning a deep coppery red before the light returns. Before understanding, such an event could send chills through observers. The Inca people of South America believed that during a lunar eclipse, a giant jaguar was attacking the moon, and that its reddish colour was the beast's bloodstains, or the blood of the moon itself. To protect their lunar goddess, they would shout and clang weapons, hoping to scare the jaguar away. In other parts of the world, people rang bells, banged pots, or offered prayers during lunar eclipses, fearful that the moon which lights their night might vanish forever. Of course, the moon always returned to its full shine in due time, restoring order to the night sky and relief to those watching below. The moon is Earth's closest celestial neighbour, and as such, it has exerted a palpable influence on our planet. Ancient observers who lived by the sea noticed that the ocean's tides, rising and falling twice a day, seemed to follow the moon. The highest tides came when the moon was full or new. There was mystery in this pull of the moon on water, as if the moon were a divine hand subtly lifting and lowering the great seas. We now understand that this is indeed the moon's gravity at work. Though the moon is small, its gravitational tug is enough to draw a bulge of water toward it as Earth spins, causing the oceans to rhythmically swell and ebb. The moon and Earth are gravitational partners locked in an ancient dance, the moon circling us roughly every 27 days and pulling on us as it does. The moon's gravity even helps stabilize the tilt of Earth's axis, ensuring that our seasons change in a steady, gentle cycle over millennia. Without the moon's steadying presence, our planet might wobble more wildly, leading to chaotic shifts in climate over long periods of time. In a very real sense, our moon has been a protector of life on Earth, its influence quietly guiding environmental rhythms that early humans depended on. What is this bright orb, truly? For a long time, people could only guess. To the eye, the moon's face shows dark and light patches. Early astronomers thought the dark areas might be seas or oceans on the lunar surface, giving them the name Maria, Latin for seas. We now know they are vast plains of ancient solidified lava. Long ago, however, even suggesting the moon was made of ordinary matter was radical. One Greek philosopher, Anaxagoras, taught that the sun and moon were not gods at all, but stones. The sun, a white-hot, glowing rock, and the moon, a more modest, earthy rock, reflecting the sun's light. This bold idea was shocking to his contemporaries. He was said to have been punished for stripping the moon of its divinity. Yet he was essentially right. The moon does not shine by its own light. It is a great ball of rock and dust, shining only by reflecting the distant sun. It wasn't until the early 17th century that humanity truly saw the moon's surface for what it was. In 1609, the Italian scientist Galileo Galilei turned one of the first telescopes toward the moon. Through that slender tube of glass, the moon's smooth glow resolved into dramatic light and shadow. Galileo saw jagged mountain ranges and deep craters pockmarking the moon's surface. He watched the sunlight catching the tops of lunar mountains, while valleys remained in darkness, just as morning sunlight touches mountain tops on Earth before the valleys below. Here was stunning evidence that the moon was a world of solid ground and rugged terrain, not a perfect ethereal orb. The moon, it appeared, was as tangible as Earth, full of valleys and peaks. This discovery upended long-held beliefs and further blurred the line between our world and the heavens. If the moon had geography, perhaps it was not so different from our own world. With time and continued observation, we learned more of the moon's secrets. We measured its size and distance, about a quarter the diameter of Earth, and roughly 384,000 kilometers away on average. We discovered it is bound to us by gravity in such a way that it keeps the same face turned toward Earth at all times. For countless generations, no one had ever seen the moon's far side. It remained a mystery, hidden until spacecraft finally ventured there in the 20th century. The moon's slow rotation, exactly synced with its orbit, a state called tidal locking, means that all those familiar features, the man in the moon, the imagined rabbit, the dark Maria, are on the hemisphere that perpetually faces us. The other side of the moon stayed unknown, fueling imagination with the idea that perhaps gods or monsters or entire kingdoms might reside there unseen. Modern science has unravelled the moon's dramatic origin story. Our moon likely formed as the aftermath of a cosmic cataclysm billions of years ago. In the early youth of the solar system, a Mars-sized protoplanet collided violently with the young Earth. This colossal impact shattered the proto-Earth and flung a huge amount of molten debris into orbit. That debris, encircling Earth, eventually coalesced under its own gravity to form the moon. In essence, the moon is made of Earth's own flesh and bone, rocky material from Earth reassembled into a new, smaller sphere. This theory, borne out by the composition of moon rocks brought back by astronauts, explains why Earth and Moon are so like a pair. We are, in a sense, a double planet, our fates entwined from the beginning. The Moon's existence speaks to the violence and creativity of the early solar system, when worlds were still forming amid chaos. Over the eons, the Moon has been slowly drifting away from Earth at a rate of only a few centimeters per year. It's a tiny motion, imperceptible in a human lifetime, but over millions of years, it adds up. When the first primitive humans looked up, the Moon was slightly closer, and thus appeared a bit larger in the sky than it does for us. And in the far future, it will appear smaller. In fact, there will come a time when the Moon will no longer perfectly cover the Sun during eclipses. Right now, in this epoch, the Moon and Sun have an extraordinary coincidence of size and distance. The Moon is about 400 times smaller in diameter than the Sun, but also about 400 times closer to Earth than the Sun is. This makes the Moon and Sun look almost the same size in our sky, allowing the Moon to just barely blot out the Sun in a total solar eclipse. Ancient peoples could not have known the geometry behind that breathtaking sight, but they marvelled at it nonetheless. In ages to come, as the Moon inches farther away, total solar eclipses will cease. The Moon will appear too small to cover the Sun completely. Ours is a fortunate time where the cosmic ballet yields such a spectacle. Throughout history, the Moon remained distant, unreachable, a lantern hanging in the sky that we could admire but never touch. Yet it beckoned to us in myths, in art, and eventually in science fiction and engineering plans. Finally, in the modern era, that dream was realized. Humans built great ships of steel and fire and dared to cross the 250,000 miles of emptiness to reach our lunar neighbour. In 1969, for the first time, human footsteps pressed into the Moon's powdery soil, fulfilling an ancient dream. Those astronauts found no palaces or gods, only silent grey plains and craters, yet the achievement was more wondrous than any myth. They brought back pieces of the Moon, literally carrying part of another world in their hands, and confirmed its origins and history. They left boot prints and a fluttering flag that stand in the airless stillness as testament to human curiosity. Even now, on a clear night, when we look up at the Moon, we can appreciate it on multiple levels. We know it for what it is, a fellow traveller through space, born of the same cosmic calamity that gave birth to Earth's own form. We understand why it shines and how it influences our planet. But we also feel what our ancestors felt, a sense of companionship in the sky, a gentle light in the darkness that has comforted and fascinated us across the ages. The moon's beauty is undiminished by knowing its craters and mountains. In fact, understanding its story makes its presence even more profound. Bathing in its pale glow, we feel a connection to all those who have stared at this same moon long before us. Its light links us to our past and shines on our future. As the night passes, the moon eventually sinks toward the horizon, and darkness begins to yield. In the east, a faint glow announces that dawn is coming. The silvery shadows of night retreat as the sky brightens. The tranquil dominion of the moon gives way to the brilliant arrival of the star that rules our day, the sun. Dawn breaks, and with it comes the triumphant arrival of the sun. The first rays of daylight banish the chill and darkness of night. In ancient times, people would turn their faces to the east and feel the warmth of the rising sun on their skin, grateful for its return. Every day, this brilliant orb climbs the sky, a dependable giver of light and life. It is no wonder that nearly every culture in history revered the sun as a powerful deity or a life-giving force. Without the sun's light, crops would not grow, cold and darkness would reign, and life as we know it could not survive. The sun truly is the heart of our world's existence. In the imaginations of our ancestors, the sun took on divine form. To the Egyptians, the sun was the god Ra, who sailed across the sky each day in a golden boat, bringing daylight to the world, and journeyed through the underworld at night to be reborn at dawn. In Japan, they tell of Amaterasu, the great sun goddess, whose radiance brings light and warmth to the land. When she once hid herself in a cave out of anger, the world was plunged into dark winter until she emerged again. The Aztecs of Mexico offered rich sacrifices to the sun, believing that its strength needed to be nourished with blood so that it would rise each morning. In cultures everywhere, the sun was recognized as the ultimate source of power. It governed the time of waking and sleeping, of planting and reaping, and it stood as a symbol of life's victory over the shadows. Yet the sun could also be a fierce and fearsome force. In the height of summer, or in arid deserts, its relentless glare could wither plants and parch the land. Civilizations learned to respect the sun's more destructive side. Droughts and heat waves were seen as expressions of the sun's wrath or sorrow. Myths often reflected this dual nature. The Greek tale of Phaethon, the son of Helios, tells of how he tried to drive his father's sun chariot, but lost control, nearly burning the earth before Zeus struck him down with a thunderbolt. It was a cautionary story of the sun's immense power, suggesting that only a skilled god could guide the solar fire safely across the sky. Despite the dazzling brightness that forbids direct gaze, humans have long studied the sun's motions and effects. Our ancestors built their lives around the cycle of the sun. They marked the year by its position. The winter solstice, when the noon sun hangs its lowest and daylight is briefest. The summer solstice, when it soars highest and days are long and bountiful. The equinoxes, when day and night balance as the sun rises due east and sets due west. Monuments from Stonehenge to Machu Picchu were aligned to these solar turning points, serving as massive calendars in stone. When the sun reached just the right spot on the horizon, shining through a temple doorway or over a heelstone, it signaled a change of season and the time for ritual celebrations or agricultural labours. The sun's regularity was both comfort and key to survival. In that reliability lay a sense of order in the cosmos. But there were moments when the sun's light was not so reliable. most dramatically during solar eclipses. On rare occasions, the moon slips directly between Earth and Sun, and daylight turns eerie. Birds fall silent, confused by the sudden twilight at noon, and a strange coolness descends. Ancient peoples often reacted with alarm and fervent prayer at these times, fearing the sun was being swallowed or extinguished. They banged drums and shouted to scare away whatever monster might be devouring their mighty sun. And always, after a few minutes, the sunlight returned as the moon moved on. Such events left strong impressions. They reinforced how vital the sun's light was, how frightening even a brief interruption could be, and how deeply people yearned for the sun's safe return. Over time, astronomers learned to predict eclipses, transforming terror into awe. Instead of panicking, some later sky watchers could stand in the moon's shadow, knowing the cosmos was simply playing out its celestial geometry. What is the sun, truly? To the ancients, it was a golden disk, a chariot of fire, an all-seeing eye in the sky. Early philosophers like Anaxagoras in Greece ventured a bold idea, that the sun was not the chariot of a god, but a fiery stone, a vast ball of incandescent matter far away. This was closer to the truth than anyone else of his era guessed, though his views were dismissed as impious at the time. For centuries, the true nature of the sun remained elusive. It was so brilliantly bright that one could not safely look at it to discern any details. It appeared as a perfect, pure light, flawless and unchanging. That image persisted until the early 17th century, when Galileo and other astronomers began observing the sun indirectly by projecting its image through telescopes. To their surprise, they saw that the sun's face was marred by dark spots that would appear and disappear over days and weeks. These sunspots drifted across the solar disk, showing that the sun rotated on its axis roughly once a month, and that it was not an incorruptible, unchanging orb, but a dynamic, blemished star. The discovery of sunspots was shocking to some, but it offered a tantalizing hint. The sun was a celestial body that obeyed natural laws and had a character of its own. As science advanced, we learned what makes the sun shine. The sun is not a burning coal or wood fire. If it were a mere flame, it would have burned out long ago. Instead, it is a colossal sphere of superheated gas, plasma, held together by its own gravity. Deep in its core, at temperatures of about 15 million degrees and crushing pressure, hydrogen atoms are fused into helium atoms. This nuclear fusion releases immense energy. Every second, the core of the sun converts about 600 million tons of hydrogen into helium, releasing energy that slowly radiates outward. After a journey of many thousands of years bouncing through the dense inner layers, this energy reaches the surface as light and heat. Finally, it streams out into space as the sunshine that warms our faces, feeds our crops, and fuels our world. When you stand in sunlight, you are feeling energy that was set free in the heart of the sun long ago and travelled 150 million kilometres across space to reach Earth. The scale of the sun is difficult to fathom. It contains 99.9% of all the mass in the entire solar system. More than 1 million Earths could fit inside the sun's volume. What looks to us like a bright disk in the sky is actually an enormous blazing globe of gas, about 1.4 million kilometres across. Its surface is a sea of boiling, convective fire, with tongues of flame, great loops of plasma, arcing high above in what are known as prominences. Yet for all its ferocity, this ongoing stellar furnace has been steady enough to nurture life on Earth for billions of years. The sunlight we depend on is remarkably constant, varying only slightly over decades. The sun gives us day-to-day warmth and light, but also drives our planet's climate and weather patterns over eons. The sun's energy is the origin of almost every form of energy we use. Ancient peoples may not have understood photosynthesis, but they knew the sun made the crops grow. Indeed, every green leaf is a solar collector, turning sunlight into food and oxygen. Forests store the sun's energy, which we later burn as wood or even as coal and oil that formed from ancient life. The breeze on a summer day, the clouds and rain, all are moved by heat from the sun, fueling wind currents and the water cycle. In these ways, the sun is truly the heart of life's ecosystem. It is no coincidence that many creation stories start with the appearance of light. Our Earth orbits the sun at just the right distance, about 150 million kilometers away, a distance we call one astronomical unit. At this range, our planet receives enough warmth for liquid water and life, but not so much as to boil the seas away. Had Earth formed much closer to the sun, it might have become a barren furnace like Venus. Much farther, and it would be a frozen wasteland. We live in a fortunate, temperate zone where the sun's gifts can be balanced and gentle. Early scholars like Aristarchus, noticing the sun's comparative enormity and brilliance, even speculated that Earth might orbit the sun rather than the other way around, a revolutionary idea that would take nearly 2,000 years to be widely accepted. Just as the sun's light nurtures life, its occasional wrath can remind us of its power. Now and then, dark sunspots pepper its face in great numbers, and tremendous flares erupt, hurling charged particles into space. When these solar storms sweep past Earth, they can stir our planet's magnetic field and ignite shimmering auroras in the polar skies. The aurora borealis and australis, the northern and southern lights, are nature's light shows, powered by the sun's restless activity. A beautiful reminder that the sun's reach extends far beyond the gentle light of day. To our distant descendants, such flares might be signals to watch, especially as humanity steps further into space. But for our ancestors, the subtle cycle of sunspots went unnoticed, and the auroras were mysterious spirits dancing in the sky. Through the centuries, humanity's view of the sun evolved from a chariot of gods to a gigantic, nuclear-fueled star. We now know that our sun is one of countless stars in the cosmos, a rather ordinary star, in fact. But to us, it is unique and precious. It is the only star that directly warms our faces and sustains life in our gardens. The realization that the stars at night are other suns came slowly, and it profoundly altered our understanding of the universe and our place within it. The sun was demoted from a deity to a star among billions. Yet in another sense, it remained as glorious as ever, a beacon of life in the vast darkness. The sun anchors our solar system with its gravity. Around it orbit all the planets, from scorched Mercury to distant Neptune, as well as countless asteroids and comets. It is the central hub of a vast celestial family. As we circle the sun, we ride along in a grand cosmic dance governed by this star's pull. Year after year, century after century, Earth and her sister planets trace their paths, held by the sun's invisible embrace. Like all stars, the sun has a lifespan. It formed about 4.6 billion years ago from a collapsing cloud of gas and dust, igniting its thermonuclear fire in the process. It has been shining steadily since long before any life appeared on Earth. It will continue to shine for roughly another 5 billion years. But it will not burn serenely forever. In the very distant future, as it exhausts its core hydrogen fuel, the sun will swell into a red giant, growing so large that it will likely engulf Mercury and Venus and sear Earth with intense heat. The oceans will evaporate, and life, if it still exists by then, will have to escape to farther worlds. That fate, however, lies unimaginably far ahead of us. For now, and for many ages to come, the sun will remain a steady beacon. Each sunset, as the sun dips below the horizon in a blaze of colours, our ancestors felt a mixture of reverence and assurance that it would rise again. Each dawn, as golden light spilled across the land, was a renewal. Even now, knowing what we do of nuclear fusion and stellar life cycles, a sunrise can inspire us with hope and a sense of rebirth. The sun connects us across time to all who have ever lived under its light. Its daily path is a thread running through the tapestry of human history, binding our stories together. As the day star that makes life possible slips out of sight each evening, we remember that it has not truly vanished. It shines on, just beyond our view, until morning comes again. And while the sun is above us, we live in its warmth and glory, children of the light. When it departs, we find ourselves once more under the canopy of night, where other lights, farther and fainter, prick the darkness. In that night sky, the planets, those wandering stars that share our sun's light, begin to reveal themselves. As twilight deepens after the sun's farewell, tiny sparks emerge, planets shining with the reflected glow of the sun, beckoning our curiosity. The stage is set to journey next to these wandering stars, the planets, and explore the rich stories they carry as companions of our life-giving sun. As dusk deepens after sunset, points of light emerge one by one in the sky. Most are distant stars, but a few are different, steadier in their glow and not twinkling as stars do. These are the wandering stars, the planets, coming into view. To ancient observers, the planets were among the most intriguing of all heavenly objects. Unlike the multitude of fixed stars that rose and set in unison night after night, the planets moved at their own pace, each tracing a unique path against the stellar backdrop. Sometimes they even reversed direction for a time, looping a loop in the heavens before continuing on their way. The Greeks called them planetai, meaning wanderers, a name that has endured through the ages. Each of these wandering lights was associated with a deity. For what else could such erratic and powerful lights be but gods roaming the night? Indeed, the names we use for the planets today echo those ancient gods. The swiftest planet was named Mercury, after the Roman messenger of the gods, known for his speed. The brightest and most radiant was named Venus, after the goddess of love and beauty. The red, fiery-looking planet was Mars, named for the god of war. The largest and most magnificent became Jupiter, after the king of the gods himself. And the farthest one, visible to the naked eye, moving with a slow, solemn grace, was Saturn, elder god of time and harvest. In other cultures, similar associations were made. The Babylonians saw the same bright Venus as Ishtar, goddess of love and war, Mars as Nergal, their god of conflict, Jupiter as Marduk, chief of their pantheon. To the Maya, Venus was particularly significant. They tracked its rising and setting meticulously, timing wars and ceremonies to its cycle. These wandering stars were not mere lights. They were omens, guides, and characters in the grand celestial story. One by one, let us visit these planets and see what stories they hold, both the ancient myths and the scientific marvels we have since discovered. Closest to the Sun, and hardest to glimpse, is Mercury. This tiny world darts quickly across the twilight sky, never straying far from the Sun's glare. Many times, Mercury can only be seen for a brief moment, low on the horizon at dawn or dusk, before it follows the Sun beneath the horizon or is lost in the brightening day. Because of its elusive, fleeting appearances, ancient astronomers found Mercury enigmatic. To the Romans, its rapid movements recalled the swift messenger god Mercury, Hermes to the Greeks, who flew on winged sandals. Fittingly, the planet Mercury completes a race around the Sun in just 88 Earth days, the shortest year of any planet. Mercury's personality in myth was that of a quick and clever god, and physically, the planet lives up to that with extremes. It is the smallest of the major planets, a little bigger than our moon, and like the moon, its surface is pockmarked with craters from countless meteor impacts. Locked in a tight orbit close to the Sun, Mercury endures intense conditions. Daytime on Mercury is a furnace, with the Sun glaring more than 3 times larger in Mercury's sky than it does from Earth, baking the rocky surface to temperatures that can melt lead. But Mercury rotates very slowly. Its day, one full turn on its axis, lasts about 59 Earth days, so nightfall is long and frigid. When the Sun finally sets on Mercury, the heat radiates away into space, and the temperature plunges hundreds of degrees until the ground is colder than Antarctica's ice. Mercury knows both searing heat and bitter cold, each in their turn. It has almost no atmosphere to distribute the heat or buffer the cold, so the contrast is stark. In Mercury's story, we find a barren, rocky world that has survived billions of years of sunfire and cosmic bombardment. Its surface has long since solidified and quieted. There are no active volcanoes or flowing rivers, only the silent record of ancient impacts and long-ago geological shifts. Tall cliffs run for hundreds of kilometers across Mercury's face. These are scars from when the little planet's interior cooled and shrank, wrinkling the surface like a dried apple. In the mythology of Rome, Mercury was a fleet-footed herald. In the reality of our solar system, Mercury is a scorched and airless little globe, forever hurrying around the Sun, as if dutifully delivering a cosmic message again and again. And yet, catching sight of Mercury in the evening glow, knowing the inhospitable world it truly is, one can still appreciate why the ancients found something mercurial, elusive and quicksilver, in that moving point of light. Next comes Venus, Earth's twin in size, but certainly not in character. Venus shines with a steady, pearly brilliance that outshines every other star or planet in the night sky. Only the moon can outshine Venus. For that reason, Venus has always captivated human eyes and hearts. The Romans named it after Venus, their goddess of love and beauty, Aphrodite to the Greeks. To the Maya and other peoples, Venus was a celestial omen, watched as a herald of events on Earth. In some traditions, Venus was a dual entity, the morning star and the evening star, appearing either just before sunrise or just after sunset. For a long time, people didn't realize that these two bright appearances in different parts of the sky were the same object. The Greeks called the morning star Phosphorus, the light bringer, and the evening star Hesperus, thinking them distinct. Only later did they understand both were Venus, whose orbit brings it alternately to the east or west of the Sun. This realization must have been profound. The goddess of morning and evening were one and the same. If Mercury is difficult to spot, Venus is impossible to miss when it's in the sky. It gleams like a miniature moon. Ancient poets described it as a jewel, a torch of heaven. But what lies beneath that lovely glow? Venus is cloaked in thick clouds that make it so reflective. For centuries, those clouds hid the planet's surface from view, so imaginations ran wild. Some speculated Venus might be a lush paradise behind its veil of clouds, a tropical sister world to Earth. That illusion was shattered when we gained the technology to peer through the clouds with radar and to send spacecraft there. Instead of a second Eden, we found a vision of hell. Venus's blanket of clouds is made not of water vapor, but of sulfuric acid. Its atmosphere is a crushing stew of carbon dioxide, nearly 100 times denser than Earth's air at ground level. This heavy atmosphere has triggered a runaway greenhouse effect, trapping the sun's heat. The result? Venus's surface roasts at around 475 degrees, 900 degrees, hot enough to melt lead, day and night, pole to pole. The air pressure at the surface is so high that standing on Venus would feel like being 900 meters deep under the ocean. The landscape of Venus, mapped by radar, is a dry, desolate expanse of volcanic plains and deformed mountains. There are volcanoes larger than any on Earth, and vast fields of lava, indicating that Venus was once highly volcanic, and some of those volcanoes might still quietly rumble under the suffocating sky. Strangely, Venus rotates in the opposite direction of most planets, and incredibly slowly. A day-night cycle on Venus, sunrise to sunrise, lasts about 117 Earth days, meaning the sun rises only 2 or 3 times in a Venusian year. In effect, Venus turns backwards, so on Venus, the sun would appear to rise in the west and set in the east. Why this is so is a mystery, though it hints at some ancient colossal collision or gravitational quirk that flipped the planet's spin. How ironic that the planet named for the goddess of love is wrapped in caustic clouds and crushing heat. Yet Venus holds a fascination, partly because it is so much like Earth in size and gravity, and partly because it shows how dramatically different an Earth-like planet can become. Through Venus, we see a kind of shadow of Earth's future, if greenhouse warming were taken to an extreme, reminding us that planetary fates can diverge greatly. In the twilight sky, though, Venus still appears serene and beautiful, a brilliant diamond that has inspired love songs, navigation lore, and fervent prayers. The Aztecs watched Venus for omens, the Greeks and Romans for romance, and today we watch it with both scientific curiosity and enduring admiration for its splendor. Beyond Earth's orbit lies ruddy Mars, the red planet. To the naked eye, Mars appears as a bright, reddish-orange star, noticeably redder than any true star in the sky. Its hue, reminiscent of the glow of embers or blood, led ancient peoples to link it with war and conflict. The Romans named it Mars after their god of war, Ares to the Greeks, and in many other cultures, Mars bore the name or symbolism of a warrior or a bringer of ill fortune. To Babylonian astrologers, the redness of Mars signified fire and war. They called it Nergal, a deity of destruction. The association was universal. Something about that blood-red dot seemed ominous and fierce. Mars, in myth, was a god to be propitiated or feared. But the real Mars is a world both inviting and inhospitable in turn. Smaller than Earth, about half its diameter, Mars is a rocky planet with a thin atmosphere. Its surface is a desert stretching under a salmon-pink sky. Iron oxides essentially rust, in the soil give Mars its distinctive colour. Long ago, Mars was active with volcanoes and flowing water. Today, it appears frozen in time, a barren realm of dust storms and ghostly dry riverbeds. Giant volcanoes tower over the Martian plains. Olympus Mons, the tallest of them, rises nearly 22 kilometers high, 3 times the height of Mount Everest, making it the largest volcano in the solar system. We've found immense canyons as well, like Valles Marineris, which stretches across Mars's equator and would span the width of the United States, its chasms going down miles deep. These features hint at a dramatic past. Perhaps the most captivating aspect of Mars is the evidence that it once had liquid water. Ancient river channels and delta formations are etched into its terrain. Rovers and orbiters have found minerals that only form in liquid water and signs of ancient lakes in Mars's craters. This suggests that billions of years ago, Mars was warmer and had a thicker atmosphere, enough for rain to fall and rivers to run. If true, that raises one of the great tantalizing questions. Did life ever spark on Mars in those wetter times? For now, Mars appears lifeless on the surface. Its atmosphere is over 95% carbon dioxide, but extremely thin, about 0.6% of Earth's atmospheric pressure, offering scant protection from cosmic radiation or the sun's ultraviolet rays. Any surface water has long since evaporated or frozen into underground ice. Still, scientists suspect that microbial life could have once taken hold when Mars was more clement, and perhaps some remnants survive in protected niches underground. Mars today is a harsh world. Temperatures swing wildly from a comfortable 20 degrees, 68 degrees, at noon near the equator in summer, down to 100 degrees, 148 degrees, on the same night. Dust storms sometimes engulf the entire planet in reddish haze. The sky often has a butterscotch tint due to fine dust suspended in the air. 2 small, misshapen moons, Phobos and Deimos, aptly named Fear and Dread, the companions of the war god, circle Mars. They are likely captured asteroids, tiny and irregular, appearing only as small blobs against the sky, even from Mars's surface. Despite its barrenness, Mars has always held a special place in human imagination. It is the most Earth-like planet in our solar system in many ways, and over the centuries, it has been a canvas onto which we project our hopes and fears about life beyond Earth. In the late 19th century, some astronomers, looking through early telescopes, believed they saw linear markings that they called canals on Mars, imagining an alien civilization desperately irrigating a dying world. That turned out to be an illusion, but it spurred popular fascination. Mars became the setting for countless stories of extraterrestrial adventure or invasion. In the 20th and 21st centuries, we sent spacecraft to finally look up close, revealing a world both stark and stunning. We found no Martian warriors, only craters and rocks. Yet we also found a world that once had the potential for life. Our robotic explorers have driven across its plains and climbed its hills, effectively extending human curiosity to that distant red dot, once thought to be an omen of war. Mars, named for the god of war, has ironically become a symbol of exploration and the search for life. Its story teaches us about transformation, from a possibly life-friendly world in the past to the cold desert we see now. And in that transformation lies a warning and a wonder. The war god's planet is quiet now, but it still fires the human spirit with the challenge. Could life take root there again, in the future, perhaps carried by us? For now, Mars hangs in our night sky, a reddish beacon that has guided ancient calendars, inspired modern science fiction, and beckoned every generation to ponder the possibility of neighbours out in the cosmic ocean. Farther out, we leave behind the inner rocky worlds and enter the realm of giants. The first of these is Jupiter, the monarch of planets. Even from Earth, Jupiter shines brightly, often outshone only by Venus and the Moon. It has a creamy white-yellow glow, and through a small telescope, one can see it as a disk crossed by dark bands. The ancients knew it as the greatest wanderer, moving sedately across the sky, taking nearly 12 years to complete one loop through the constellations. The Romans named it for Jupiter, Jove, the king of the gods, known in Greek as Zeus. This name was fitting. Everything about Jupiter is colossal. It is by far the largest planet in the solar system, more massive than all the other planets combined, a true giant ruling over its domain. Jupiter is a gas giant, a type of planet unknown to the ancients except through what they saw in the sky. If one could peel back Jupiter's curtain of clouds, there would be no solid ground to land on. Instead, what appears as its surface is the tops of deep cloud layers in an atmosphere made mostly of hydrogen and helium gas. The planet likely has a dense core buried deep inside, but above that core lie tens of thousands of kilometers of fluid, pressurized hydrogen, gradually transitioning to the gaseous atmosphere we see. Visually, Jupiter is stunning. Modern observations show its cloud tops streaked with bands of white, yellow, tan, and reddish-brown. These stripes are fiercely windy jet streams wrapping around the planet, where ammonia clouds form the lighter bands and other compounds color the darker bands. Scattered between these bands are immense swirling storms, including the famous Great Red Spot, a gigantic oval storm bigger than Earth, which has been raging for at least 300 years, ever since astronomers first observed it through telescopes. In mythological terms, Jupiter, Zeus, was a protector and punisher with a thunderbolt in hand. Fittingly, planetary Jupiter wields tremendous power in the solar system. Its gravity dominates the space around it, shepherding a retinue of dozens upon dozens of moons. At least 79 known moons orbit Jupiter, resembling a miniature solar system of its own. The 4 largest moons, first seen by Galileo in 1610, are each unique worlds. Io, racked by volcanoes erupting fountains of sulfur. Europa, a smooth, icy globe suspected to hide a deep ocean beneath its frozen crust. Ganymede, bigger than the planet Mercury and laced with bright frost and dark terrain. And Callisto, an ancient cratered ball of ice and rock. The discovery of those moons in the time of Galileo was revolutionary. It showed not everything revolves around Earth, hinting that Jupiter had its own subsystem. For Galileo and his contemporaries, seeing those stars move around Jupiter night after night gave a first glimpse of cosmic order beyond Earth's dominion. Jupiter's gravitational influence is a double-edged sword. On one hand, it likely helped shape the solar system's development and may act as a shield, its strong gravity flinging away or capturing many comets and asteroids that might otherwise threaten the inner planets. For instance, when comet Shoemaker-Levy 9 slammed into Jupiter in 1994, the giant absorbed impacts that would have been catastrophic had they hit Earth. On the other hand, Jupiter's gravity can also perturb asteroids from their orbits, sending them sunward. It is largely responsible for the asteroid belt between Mars and Jupiter remaining bits and pieces rather than forming another planet. Jupiter's tug kept those rocks from coalescing. From Earth, people have long marveled at Jupiter's stately presence. In astrology, Jupiter was deemed the great benefice, associated with luck and expansion, perhaps echoing the planet's vastness and the protection it seemed to afford. Scientifically, Jupiter has been a source of wonder ever since we glimpsed its cloud belts and moons. Space probes have visited it, revealing lightning in its clouds, auroras dancing at its poles, and a magnetic field 20,000 times stronger than Earth's, forming a magnetosphere that stretches millions of kilometers and even envelops some of its moons. The king of planets truly wears a crown of invisible force. When we gaze at Jupiter on a clear night, we see a point of light that has captivated humankind for millennia. We see the same planet our distant ancestors did, one that they perhaps felt governed high affairs of state or weather. Now we know it as an enormous spinning ball of gas, with storms bigger than continents and moons that might harbour life's precursors. Jupiter's story is one of superlatives. Biggest, fastest spinning. A Jupiter day is just 10 hours. Most mooned, mightiest. As our journey moves further out, we keep in mind this great guardian and monarch of the outer solar system, shining watchfully in the heavens like the patriarch of a planetary family. If Jupiter is the king of the planets, Saturn is the elegant queen, adorned with a spectacular crown of rings. Saturn was the most distant planet known to antiquity, taking nearly 30 years to traverse the sky and return to the same position relative to the stars. It gleams with a soft golden light, less bright than Jupiter, but steady and imposing. The Romans gave it the name Saturn, their god of time and agriculture, equivalent to the Greek Cronus, father of Zeus. Saturn's slow progress across the heavens, slowest of the visible wanderers, befitted the god of time, often depicted as an aged deity. In astrology, Saturn came to symbolize constraints and wisdom that come with age, perhaps influenced by its steady, unhurried path. To the ancients, Saturn was a mysterious dot at the edge of vision. Not until the invention of the telescope did its true wonder reveal itself. In 1610, when Galileo first observed Saturn with his crude telescope, he was perplexed. He reported seeing Saturn as triple-bodied or having ears. His instrument wasn't sharp enough to discern the rings properly. It took later astronomers, like Christian Huygens in 1655, to recognize that Saturn is surrounded by a thin, flat ring. Now we know Saturn's rings are one of the most beautiful sights in the solar system, broad, bright, and composed of countless icy particles orbiting Saturn like a myriad tiny moons. They form concentric circles, separated by gaps, extending outwards tens of thousands of kilometers from the top of Saturn's atmosphere. Yet they are astonishingly thin, only a few tens of meters thick in places. From afar, they look solid and serene, but up close they are dynamic, with particles ranging from dust grains to boulders racing around the planet. The planet Saturn itself is a gas giant, second only to Jupiter in size, about 9 times Earth's diameter. It's less dense than water. In fact, if you could find a bathtub big enough, Saturn would float. A fanciful image, though of course such a scenario is impossible. Saturn's pale gold appearance comes from its cloud layers, which contain ammonia crystals and other substances. Its weather is not as vividly banded as Jupiter's, but storms do occur. Occasionally a great white spot erupts in Saturn's clouds, a tempest that can wrap around the planet. Saturn spins quickly. A day is about 10.7 hours, flattening it noticeably at the poles. Its rapid rotation and internal metallic hydrogen layer generate a strong magnetic field, though weaker than Jupiter's. Saturn's entourage of moons is rich and varied. The largest, Titan, is an extraordinary world in its own right, bigger than planet Mercury and shrouded in a thick orange atmosphere. Titan's air is mostly nitrogen, like Earth's, but frigid with methane clouds. On Titan's surface, rivers and lakes of liquid methane and ethane have been discovered, making Titan the only other body in the solar system known to have liquid on its surface today, though it's not water, but methane, due to the far colder temperatures out there. This discovery in modern times has been breathtaking. It suggests geology and possibly prebiotic chemistry in Titan's hidden environments. Other notable moons include Enceladus, an icy moon that ejects geysers of water vapor and ice from its south pole, evidence of a subsurface ocean kept warm by tidal forces. In myth, Saturn, Cronus, devoured his children, but in the sky, the planet Saturn graciously shares its realm with at least 80 moons, nurturing them within its influence. The imagery and symbolism of Saturn's rings have not been lost on humanity. When they were first clearly seen through 17th century telescopes, they seemed almost too perfect to be natural. Some early astronomers hypothesized Saturn was 3 planets close together, or a planet with arms. Now that we understand them, the rings remain a source of wonder and a favorite target of space probes and backyard telescopes alike. They remind us that the universe still holds beauty that can surprise us. Saturn's serene majesty, a golden globe encircled by ethereal rings, often leaves viewers speechless upon first sight through a telescope. It has the appearance of a celestial jewel box, unique in our skies. In ancient times, Saturn marked the boundary of the known solar system. Beyond it lay nothing but the realm of fixed stars, or so it seemed. Saturn's slow journey was the outermost beat in the cosmic rhythm visible to human eyes. To stand under a clear night and locate Saturn, knowing what we know now, is to time travel in a sense, to appreciate how our ancestors looked at that pale dot and saw the edge of creation, while we look and know that beyond it orbit more worlds hidden from their view. Saturn, the old god, taught patience and humility. Saturn, the planet, invites us to reflect on time and change. Its rings, possibly the remnants of a shattered moon or a comet that strayed too close, may last only a few 100 million years more before dispersing. A reminder that even the most seemingly eternal features in the sky have life cycles. But for now and generations to come, Saturn graces our night sky as a sublime marvel. For the ancient stargazers, Saturn marked the outer boundary of the known universe. Little could they imagine that beyond Saturn, more planets circled the Sun in the deep reaches of space. In modern times, telescopes revealed Uranus, discovered in 1781, and Neptune, 1846, and later Pluto, 1930, at the fringe of the solar system. These carried on the tradition of mythic names. Uranus, named for an ancient sky deity, is an ice giant tipped on its side, rolling around the Sun with a pale blue-green hue. Neptune, the azure planet named for the sea god, harbours supersonic winds and a large moon, Triton, that orbits opposite to Neptune's spin. Pluto, bearing the name of the lord of the underworld, is a tiny icy globe on a distant, elongated path. Though Pluto is now classified as a dwarf planet, its discovery extended the Sun's family and fired imaginations about what might lie in the Kuiper Belt, the domain of comets and frozen worlds at the solar system's edge. These outer worlds were unknown to the ancients, yet today we see them as part of our Sun's extensive retinue. Beyond the 8 classical planets, countless smaller bodies, asteroids, comets, and dwarf planets also orbit, each contributing to the story of our solar system. Where once Saturn was thought to be the final wandering star, We now know the planetary family continues outward into the darkness. The discovery of Uranus, Neptune, Pluto, and other distant objects taught us that our cosmic neighborhood is more crowded and diverse than first believed. The essence of their stories remains the same. They are fellow travelers around our sun, bound by the same gravity, illuminated by the same starlight. We have journeyed outward from the sun, visiting each wandering star in turn. Each planet has its story, deeply intertwined with human culture and curiosity. From Mercury's swift dance to distant Pluto's ghostly glide, the planets have been constant companions in our night sky, and now are destinations in our quest for knowledge. With the planets explored in our minds, we find ourselves at a new vantage point. The ancient idea of 7 heavenly bodies, sun, moon, and 5 planets, gave way to a solar system of many worlds, with Earth among them, all circling the sun. This was a profound shift in perspective. It meant that Earth, our home, is one planet among others, not the fixed center of creation. How did we come to realize this daring idea? It is time to step back in history to the moment when the sun took center stage in our understanding and changed the cosmos forever. For thousands of years, our view of the cosmos placed Earth firmly at the center. It made intuitive sense. The ground beneath us feels still, and overhead, the heavens seem to wheel around once a day. In ancient Greek and medieval astronomy alike, the prevailing model was that of a geocentric universe. Earth was the motionless hub, and the sun, moon, planets, and stars circled around it in nested crystalline spheres. This picture, refined by the astronomer Ptolemy in the 2nd century AD, became the canonical worldview for centuries. In Ptolemy's model, each planet moved on a small circle, an epicycle, that in turn moved along a larger circle around Earth. This complex system could explain, with fair accuracy, the wandering paths and occasional retrograde loops of the planets. It was intricate and somewhat clumsy, but it worked well enough to predict planetary positions and eclipse cycles. And beyond the outermost sphere of Saturn lay the fixed stars, forming a cosmic firmament. Earth, in this scheme, was the focal point of creation, the stage upon which the drama of life and the heavens played out. Yet, even in antiquity, a few thinkers had dared to imagine a different arrangement. In the 3rd century BCE, a Greek astronomer named Aristarchus of Samos proposed that it made more sense for the sun to be at the center, with Earth and the other planets orbiting it. He had observed that the sun was vastly larger than Earth. He deduced this from the geometry of eclipses and the moon's phases, and reasoned that the smaller body should orbit the larger. Aristarchus's heliocentric idea was ingenious but far ahead of its time. Without observational proof, and with the Earth's immobility seemingly obvious to the senses, his idea gained little traction. The ancient world stuck with Earth at the center, as would the scholars of the next 2 millennia. By the Renaissance, however, the accumulated observations of the sky were straining the old Ptolemaic model. Planets weren't quite where the old tables predicted. The equinoxes were slowly drifting over centuries, a phenomenon called precession. And scholars sought simpler, more elegant explanations for the cosmic order. Enter Nicholas Copernicus, a Polish astronomer and polymath, who in the early 1500s revisited the heliocentric idea. Copernicus spent decades quietly working on a new model of the heavens. In 1543, as he lay on his deathbed, his major work, On the Revolutions of the Heavenly Spheres, was published. In it, Copernicus boldly placed the sun at the center of the universe, with Earth becoming just one planet orbiting the Sun annually, while also spinning on its axis daily. The Moon he correctly kept as orbiting Earth. This rearrangement explained the retrograde motions of planets naturally. When Earth, on its faster inner orbit, overtakes a planet like Mars on the outer track, Mars appears to go backward in the sky for a time. It also logically ordered the planets by distance from the Sun, and it greatly simplified the system, though Copernicus still used some small epicycles to fine-tune his predictions, since he assumed orbits were perfect circles. The publication of Copernicus's heliocentric theory was a watershed moment, but at first it stirred more interest than outrage. Many scholars saw it as a useful mathematical model, but not necessarily a description of reality. After all, if Earth truly moved, why didn't we feel a constant wind or get thrown off into space? And if we orbited the Sun, why did the positions of the stars not noticeably shift over the year? A phenomenon known as parallax. The absence of observed stellar parallax was a strong argument for geocentrists. The stars seemed fixed in place, implying Earth wasn't moving, or that the stars were unimaginably far away for the tiny shift to be unobservable with the naked eye. Most scientists of the day reserved judgment, treating Copernicus's idea as one hypothesis among others. Over the next decades, evidence began to accumulate, favouring the sun-centred model. In 1601, the great Danish astronomer Tycho Brahe, who had compiled the most precise observations of planet positions using sighting instruments, died, leaving his data to his German assistant, Johannes Kepler. Kepler, a brilliant mathematician and a believer in Copernicus's vision, struggled with Mars's orbit, trying to fit it into Copernicus's circular orbits. After much effort, he found the breakthrough. The orbits were not circles, but ellipses, with the Sun at one focus. With this insight, Kepler formulated his 3 laws of planetary motion, published between 1609 and 1619, that described how planets move. In ellipses, sweeping out equal areas in equal times, and relating their orbital periods to their distance from the Sun. Kepler's laws finally provided a heliocentric model that matched observations with unprecedented accuracy. No epicycles needed. Still, the question remained: was this just a convenient calculation tool, or the true layout of the cosmos? Around the same time, in 1609, an Italian scientist named Galileo Galilei heard of a new invention from Holland, the telescope. He built his own and turned it to the night sky. What he observed through this small tube forever changed the heavens in human perception. In January 1610, Galileo discovered 4 moons orbiting Jupiter, now known as the Galilean moons Io, Europa, Ganymede, and Callisto. Night after night, he sketched their positions as they circled Jupiter. This was a miniature solar system in effect. Not everything revolved around Earth, because these moons clearly revolved around Jupiter. It was direct evidence that the geocentric idea had a fundamental flaw. Galileo also observed the phases of Venus. Venus showed a full set of phases: crescent, quarter, gibbous, full, much like the moon's phases. In the Ptolemaic model, such a thing was impossible. Venus's epicycle kept it between Earth and the Sun, so it could never show a full phase. But in the Copernican model, Venus orbits the Sun, and we see it from different angles, which naturally produces the full range of phases. When Galileo saw Venus as a tiny full disk, and later as a larger crescent, it was striking confirmation that Venus indeed orbited the Sun, not Earth. Galileo's discoveries, along with his outspoken support for Copernicanism, ignited controversy. The idea of Earth moving was still philosophically and theologically unsettling to many. The Church at that time held geocentrism as aligned with Scripture and the prevailing Aristotelian philosophy. In 1616, heliocentrism was formally declared contrary to Scripture by Church authorities, and Copernicus's book was suspended pending corrections. Galileo was warned not to teach it as truth. He pressed on cautiously, but eventually, after publishing a dialogue in 1632 that defended the heliocentric idea and poked fun at its opponents, he was tried by the Inquisition. In 1633, under threat of severe punishment, Galileo was forced to recant and spent the rest of his life under house arrest. The image of the aged scientist, compelled to deny what his eyes had shown him, became an enduring symbol of the struggle between new knowledge and established doctrine. Yet, the evidence kept mounting, and the ideas kept spreading. Galileo's writings circulated in Protestant Northern Europe. Kepler's laws gained acceptance among those who could do the calculations. The generation after Galileo saw the ultimate synthesis. Isaac Newton, born the year Galileo died, would in 1687 publish the Principia Mathematica, laying out the law of universal gravitation and the laws of motion. Newton provided the physical explanation that had eluded Copernicus, Kepler, and Galileo. Gravity, Newton showed, was the invisible force that kept the planets in their orbits and pulled apples to the ground. With one sweeping theory, he unified the physics of the heavens and the earth. In Newton's universe, the same force that made an apple fall also made the moon circle Earth and Earth circle the sun. This celestial dance was not maintained by crystal spheres or divine movers, but by the simple, profound rule that every object attracts every other. The Copernican revolution had reached its culmination. The heliocentric model was now grounded in physical law and predictive power. By the early 18th century, the sun-centered system was widely accepted among scientists. Earth truly moved around the sun, and the Copernican idea had won the day. The shift from an Earth-centered cosmos to a sun-centered one is often called the Copernican revolution, and rightly so. It altered not only astronomy, but the way we humans view ourselves. Many people found this upheaval disorienting, as if the comfortable, closed universe they knew had exploded into something vast and uncertain. Others found the new perspective exhilarating. Giordano Bruno, an Italian philosopher who was burned at the stake in 1600, a fate due to many heresies, including his Copernican views, had preached that the universe was infinite and that countless stars were themselves suns with their own planets and perhaps living beings. He extolled a cosmos where Earth was not the center, but one world swimming in an endless ocean of worlds. While Bruno's ideas were too radical for his time, they would later resonate as telescopes revealed the vastness of space. The heliocentric model opened the door to that possibility. If Earth is just another planet, and the Sun just a star, then might not the stars be other suns with their own planets? Might not life exist elsewhere? By moving Earth from the center, Copernicus moved us one step closer to an infinite universe brimming with possibilities. It's important to understand that accepting this new cosmology took time. By the late 17th century, most astronomers had been won over, especially after Newton's work, but it took longer for the general worldview to shift. Eventually, improved instruments did detect the tiny parallax of the nearest stars, confirming beyond doubt what Copernicus had claimed. But even before that proof, the weight of evidence and reason had turned the tide in favor of heliocentrism. The sun had taken center stage in our solar system, and with that, our understanding of the universe expanded unimaginably. We went from a finite cosmos with a sphere of fixed stars just beyond Saturn to a vision of the sun as one star among myriads in a limitless expanse. The Copernican perspective was the first domino in a chain of revelations that continue to this day. But all these developments stem from that pivotal recentering from Earth to Sun. It is a profound and poetic irony that by realizing we are not the center of the universe, we were able to discover so much more of the universe. Standing on a moving Earth, rotating at over 1,000 kilometers per hour, and orbiting the Sun at about 100,000 kilometers per hour, we do not feel our motion, but we see its effects in the rhythms of the skies, now understood. We have learned to step off our cosmic pedestal, and in doing so, have seen further and deeper than ever before. As we end this first part of our journey, we find ourselves looking up at a night sky transformed by knowledge. The moon is a world in its own right. The wandering stars are other planets, circling the sun like we do. The sun, once a golden god riding through the heavens, is a blazing star that anchors a family of worlds. And the stars themselves? They beckon with new mystery. For now we know that each is a sun, and the universe holds more suns, and perhaps more worlds, than our ancestors ever imagined. The story of how we came to understand those distant stars and the vast cosmos beyond our solar system lies ahead. With the sun at the center of our small system, we turn our gaze outward, ready to embrace the next chapter of the cosmic journey. On a clear, moonless night far from the city, the sky becomes a deep black canvas spangled with stars. Thousands of brilliant pinpoints shimmer against the dark, each a beacon of light from the far cosmos. As your eyes adjust to the darkness, more and more stars emerge, as if the universe is slowly revealing its abundance. The sight is as old as humanity, the same starry sky that captivated our distant ancestors and inspired them to wonder what those lights might be. It is a breathtaking panorama, the dome of night, filled with the glow of distant suns. For ages, people looked up and found pictures among the stars. They connected the brightest dots into shapes and figures, crafting stories to give meaning to those patterns. There was Orion, the great hunter chasing his prey across the heavens. Leo, the mighty lion. The Big Dipper, which some saw as a bear and others as a ladle or wagon. Nearly every culture wove its own legends into the constellations. To many, the stars were campfires of the gods, or the eyes of celestial beings watching over the world. Under this vast, sparkling tapestry, humans felt both awe and a sense of guidance, as if the heavens held clues to who we are. The stars, in fact, became our first compass and calendar. Travellers learned to navigate by them. The North Star, Polaris, almost fixed in the sky, guided journeys over trackless seas and deserts. Each night, Polaris reliably marks the way north for those who know how to find it. And as the Earth orbits the Sun through the year, different stars and constellations come into view with the seasons. Ancient farmers watched the heliacal rising of Sirius, the brightest star, which in Egypt heralded the flooding of the Nile. The skies told them when to plant and when the rains would come. In this way, the stars were not just distant lights, but intimate companions in the rhythm of life. If you watch a star twinkle on the horizon, you might see it flicker and dance, perhaps flashing hints of blue or red. This twinkling is caused by our own atmosphere, high-altitude winds bending the starlight subtly back and forth. It can give the illusion that the star is alive and fluttering. Planets, which shine with a steadier light, usually do not twinkle as much. Yet the playful twinkle of the stars has enchanted poets and children for generations, inspiring us to wish upon those diamonds in the sky. Only in the last few centuries have we come to understand what a star truly is. For most of human history, the nature of the stars was mysterious. Tiny points of fire, perhaps, or distant lanterns hung in the sky. Then we discovered that each star is actually a sun, a colossal sphere of incandescent gas blazing with energy. Our own sun is one of these stars, average in most respects, but it appears huge and bright to us because we live in its proximity. Those other stars are incredibly far away, so distant that even the nearest beyond our solar system is more than 4 light years off. That is, it takes light itself over 4 years to journey from there to here. Most stars are far farther still. That is why they seem like faint pinpoints. Their brilliant light dwindles to a twinkle by the time it reaches our eyes. Consider that when you look at a star, you are seeing a message from the past. The starlight that enters your eye has been traveling for years, decades, even centuries, or millennia across space. The nearest star beyond the Sun, Proxima Centauri, is about 4.2 light years away. Its light left around the time we were celebrating the new year 4 years ago. The star Deneb, one of the bright jewels of the summer sky, is about 2,600 light years distant. Its light began its journey during the height of the Roman Empire, and some stars visible to the naked eye are tens of thousands of light years away. Their glow started on its way before humans even knew what stars were. When we gaze at the night sky, we are witnessing a kind of time machine, seeing some stars as they were long before the pyramids were built, almost as if the universe is telling its history through light. Take Betelgeuse, the reddish star marking the shoulder of Orion. It lies on the order of 600 light years from Earth. The light we see from Betelgeuse tonight set out around the 15th century, the late Middle Ages, perhaps when Leonardo da Vinci was alive. Betelgeuse itself is a remarkable star, a red supergiant nearing the end of its life. If placed where our Sun is, Betelgeuse would swell beyond the orbit of Mars, engulfing Earth's path entirely. Its surface is cooler, hence its ruddy hue, but its sheer size and brightness are enormous, tens of thousands of times more luminous than the Sun. Now compare it to a star like Sirius, the brightest star in our night sky. Sirius is relatively close, just 8.6 light years away, and it shines a brilliant white blue because it is much hotter at the surface than our Sun. Look up on a winter night, and you can easily spot these color differences. Betelgeuse glowing orange-red, while Rigel, Orion's foot, and Sirius scintillate blue-white. The colors of stars are clues to their temperatures and stages in life. Blue-white stars are hotter and often younger. Red stars, cooler, or sometimes giants in old age. The variety among stars is staggering. The smallest stars, red dwarfs, are cooler and so faint that not a single one can be seen without a telescope, even though they are the most common stars in the galaxy. These diminutive stars may be only a tenth the mass of the Sun and burn their fuel so slowly that they will shine for hundreds of billions of years, far longer than the current age of the universe. On the other end are the giants and supergiants like Betelgeuse, stars that started with many times the Sun's mass. They blaze through their fuel at a furious rate and swell to immense proportions. Some, like the star Deneb, or the even more massive Eta Carinae, shine with the light of hundreds of thousands of suns. Rarest of all are the true titans, stars dozens of times the sun's mass that shine millions of times brighter. These beasts live short, brilliant lives and will end in spectacular deaths, as we'll see later. In between these extremes lies our sun, a steady, middle-aged yellow star, quietly burning its fuel and providing the warmth and light that sustains life on Earth. When you gaze up at the night sky, the stars you see are only a tiny sampling of what's truly out there. On the darkest of nights, with perfect vision, a person might see a few thousand stars scattered across the entire sky. That may sound like a lot, but our Milky Way galaxy contains several 100 billion stars. The vast majority are simply too far or too faint for our eyes to pick out. It was only when the telescope was invented that we realized just how populous the universe is. In 1610, Galileo Galilei turned one of the first telescopes to the Milky Way, that hazy band of light, and discovered it was composed of countless faint stars. Where the unaided eye saw a milky cloud, the telescope revealed star upon star upon star, more than could be numbered. Later, astronomers scanning the skies saw stars wherever they looked, in every direction, at all distances, some in dense clusters, some scattered alone. It became clear that our night sky's starry dome is but a keyhole peek into a vast stellar realm. Some of the stars our ancestors named turned out to be star clusters or nebulae on closer inspection. The Pleiades, for example, is a tight cluster of young stars in Taurus. To the naked eye on a dark night, 6 or 7 of its brightest members can be discerned, hence the old name Seven Sisters. But point a telescope or even binoculars at the Pleiades, and you'll see dozens of stars, maybe even a faint sheen of nebulous dust around them. The cluster is like a little family of stars born together, moving through space as a group. Many cultures have stories about this cluster, often about 7 siblings or friends, not knowing we actually see only the brightest ones of a much larger stellar nursery. And the Pleiades is just one cluster. The Milky Way is sprinkled with many such groups, each a reminder that stars often form in batches rather than in isolation. Indeed, stars prefer company. A great number of the points of light we call stars are actually 2 or more stars orbiting each other in a gravitational dance. These binary or multiple star systems can be so close together that they appear as one, even through a telescope, or wide enough apart to see individually. One famous example is Albireo, a star in the constellation Cygnus. With the unaided eye, Albireo looks like a single star, but through a telescope, it splits into a stunning double. One component shines golden, the other sapphire blue. They circle a common center, bound by gravity. The contrasting colors make Albireo a favorite target for stargazers, a cosmic jewel set of blue and gold. Such binary stars are common. The universe seems to love pairs and trios when it comes to stars. Over countless generations, as people observed the steady patterns of the stars, they also noticed that once in a rare while, something would change. A star that was not there before might suddenly appear, or an existing star might brighten dramatically and then fade. These were alarming and wondrous events to ancient skywatchers, who often interpreted them as supernatural omens. We now understand that they witnessed either novas or supernovas, stars in distress or dying in brilliant outbursts. One famous example occurred in the year 1054 AD. Astronomers in China and elsewhere recorded a guest star that shone brightly even in daylight for weeks. The star then vanished from view months later. Nearly 1,000 years afterward, modern telescopes identified the remnants of that explosion. The Crab Nebula, an expanding cloud of gas and dust hurled into space by a supernova. Imagine the awe, and perhaps dread, such an event would have inspired at the time, without any way to know what it meant. For the most part, though, the stars change on timescales far longer than human lives. They seemed eternal to our ancestors, the same stars rising and setting year after year, generation after generation. But we have learned that stars are born, live out their lives, and eventually die. They are not eternal at all, just long-lived beyond ordinary experience. And it is in their life cycles that the universe regenerates itself. When stars die, especially in cataclysmic supernova explosions, they seed space with the heavy elements that will become new stars, new planets, and even new life. Every bit of you, of me, of the earth itself, was forged in the heart of a star. The calcium in our bones, the iron in our blood, the carbon in our cells. Those atoms were once produced by nuclear fusion in a star's core or during a star's violent death. We truly are made of stardust. It's a poetic notion, famously articulated by astronomer Carl Sagan, and it is also the literal truth. The universe has recycled matter through many generations of stars, and that process ultimately made life possible. So as we stand here under the starlight, we do feel small. The universe is immense, and we are tiny in comparison. Yet we also feel connected to those distant suns. They are our cousins, in a sense, and our existence is linked to theirs. Humans have always felt something profound when looking up at the stars, a mix of wonder, curiosity, and longing. Over the last few centuries, we have built instruments to unravel the stars' secrets. We have learned how far away they are, what makes them shine, and even what they are made of by splitting their light into spectra. And in doing so, we found something extraordinary. Many of those stars, perhaps most, are not alone. They have planets of their own, other worlds orbiting those distant suns, just as our Earth circles the sun. The night sky, once thought to consist of just a celestial sphere holding fixed stars, has turned out to be a dynamic, expansive reality. The tiny lights above are mighty furnaces, and around them may circle new Earths, or strange worlds we've never dreamed of. The stars of the night invite us onward, urging us to explore what lies around them. Our journey now continues, moving outward from the stars themselves to the planets that accompany them. The ancient question, are there other worlds out there, has finally been answered. Yes, there are. And as we shall see, they are astonishing in their diversity. Let us venture forth to explore these other worlds, the planets beyond our solar system. For countless generations, the idea of other worlds circling those distant stars was nothing more than a dream, a topic for storytellers and philosophers. Ancient peoples may have wondered about the lights in the sky and imagined realms beyond Earth, but they had no way to know if any existed. Even as recently as the mid-20th century, we knew of only the planets in our own solar system. The question of whether planets were common around other stars was met with speculation and skepticism. Some scientists thought our solar system might be unique, or at least very rare. Others suspected that the universe might be teeming with untold worlds, waiting to be discovered. It was only in the last decades of the 20th century that technology advanced enough to begin finding these elusive planets beyond our solar system, the exoplanets. The first definitive discoveries came in the early 1990s, and they were a surprise. In 1992, astronomers detected not one, but several planets orbiting a pulsar, the rapidly spinning corpse of a star that had exploded. It was an astonishing find. Planets circling a tiny, dead star, bathed in intense radiation. Such worlds would be unlike anything we could have imagined as a cradle for life. Just a few years later, in 1995, the first planet around a sun-like star was confirmed. This planet, 51 Pegasi b, defied expectations. It was a gas giant about half the mass of Jupiter, yet it hugged its star so closely that its orbit lasted only 4 days. It was dubbed a hot Jupiter, a type of planet no one anticipated from our knowledge of the solar system. Nature, it seemed, had far more variety up its sleeve than we had guessed. From that point onward, discovery after discovery poured in. Astronomers refined ingenious methods to detect these faint, far-off worlds. One method watches for tiny dips in a star's brightness when a planet passes directly in front of it. A transit, like a moth briefly fluttering across a distant headlight. Another method listens for the slight wobble in a star's motion caused by the gravitational tug of an orbiting planet, like detecting a subtle dance. At first, only a trickle of exoplanets were found, but as instruments became more sensitive, the floodgates opened. Especially transformative was the Kepler Space Telescope, launched in 2009. It stared for years at a single patch of sky, monitoring tens of thousands of stars for telltale dimming. From its diligent gaze, we learned that planets are astonishingly common. Kepler alone added thousands of new worlds to our catalogue, revealing that on average, most stars likely host at least one planet. In the few decades since the first discoveries, we've confirmed well over 5,000 exoplanets, with new ones being added every month. These planets come in a dazzling variety of sizes, orbits, and compositions, far more variety than we see in the 8 familiar planets of our own solar system. Among these newfound worlds are some that at first seemed like misfits from a cosmic zoo. There are hot Jupiters, giant gas planets roasting so near their parent stars that their cloud tops broil at thousands of degrees, and winds whip around at thousands of kilometers per hour. On one such world, a deep blue planet discovered by astronomers, it could be literally raining molten glass from cobalt-colored skies, the glassy droplets blown sideways by furious, high-speed winds. There are planets larger than Jupiter, but orbiting so close to their stars that they are on the verge of being torn apart, their atmospheres slowly bleeding off into space like a comet's tail. In contrast, we have found super-Earths and mini-Neptunes, categories of planets that have no equivalent in our solar system. A super-Earth is a rocky world larger than Earth, sometimes with a thick atmosphere, or perhaps vast global oceans, while a mini-Neptune is a gassy planet smaller than Neptune, shrouded in dense layers of gas. We've discovered planets with densities so low, they're puffed up like cotton candy, giant worlds with the mass of a few Earths, but spread out larger than Jupiter. And we've found others as compact and dense as iron, orbiting so close to their stars that a year lasts only a few hours as they sprint around at dizzying speed. Perhaps most evocative are the worlds that remind us of home, at least in some ways. Astronomers have found planets near the size of Earth orbiting in the habitable zone of their stars, the not too hot, not too cold region, where, if conditions are right, liquid water might exist on a planet's surface. One such star, a cool red dwarf called TRAPPIST-1, hosts 7 Earth-sized planets, 3 of which lie in that temperate zone. Imagine standing on one of those distant worlds. The red sun hangs dim and ruddy in the sky, casting a perpetual twilight glow. In that sky, you might see the outlines of neighbouring sister planets, perhaps as large as our moon appears to us, because they are all so tightly packed around their small star. What a sky that would be! Multiple planets suspended in the dusky firmament, a red star lighting the landscape in hues of crimson and orange. We have also found planets in configurations once left to the realm of science fiction. Recall the iconic image of twin suns setting over Luke Skywalker's homeworld in Star Wars. In reality, we now know of planets that orbit double stars, experiencing dual sunrises and sunsets. Kepler 16b is one such world, a Saturn-sized planet discovered orbiting a pair of stars. If you stood on its surface, you would see 2 suns in the sky, perhaps one golden and one orange, dancing around each other. Sometimes they'd eclipse one another, casting peculiar double shadows on the ground. Sunset on such a world might mean watching one sun slip below the horizon, while the second sun still glows above, painting the sky in twin shades of dusk. Once the stuff of imagination, these Tatooine planets are now known to exist. The diversity of other worlds is truly breathtaking. Some exoplanets likely have skies tinted with unfamiliar colours due to exotic chemistry in their atmospheres. There are planets where a year, one orbit around the star, lasts only a few days, and others where a single year spans centuries. Some worlds hug so close to their suns that they are tidally locked, forever showing one face to their star and keeping the other face in perpetual darkness. On those, one hemisphere bakes under eternal daylight, while the opposite side freezes in endless night, with perhaps a twilight ring between them where conditions might be more moderate. There are even planets that drift alone in the dark, having been cast out of their parent systems. Rogue planets wandering the galaxy without a sun to warm them, invisible except to the keen eyes of infrared surveys. Each discovery has expanded our perspective of what a planet can be. Not long ago, planet meant the handful of familiar orbs orbiting our sun, each fairly well behaved. Now we know that was a parochial view. Planets can be far stranger, more varied, and more numerous than we ever imagined. And these thousands of confirmed exoplanets are likely just the tip of the iceberg. Our instruments today are best at finding the big, the close-in, and the unusual cases. There are undoubtedly a great many smaller, more Earth-like worlds out there still beyond our current reach, waiting to be found with the next generations of telescopes and probes. Perhaps the most profound aspect of this torrent of discoveries is what it means for the possibility of life beyond Earth. With so many planets out there, likely hundreds of billions in our galaxy alone, it seems increasingly likely that some fraction of them must have the right conditions for life. We have already identified dozens of promising candidates where temperatures and conditions might be similar to Earth's. Whether any of those have actually given rise to living organisms, we cannot yet say. But the sheer number of other worlds makes it hard not to wonder if we are truly alone, or if the universe is full of living planets, each with its own biosphere, and perhaps even its own observers, gazing back at the stars. The search has even begun to peek into some exoplanet atmospheres, using delicate measurements to detect molecules in the air of those distant worlds. We found hints of water vapour, carbon dioxide, and other gases in a few exoplanet skies. In coming years, improved telescopes might detect telltale signs of biology, perhaps an abundance of oxygen, or the subtle imprint of organic molecules in the air of a far-off planet. Imagine what it would mean to discover a world with a breathable atmosphere, blue oceans, and green continents. A second Earth, under the light of an alien sun. It's a thought that has driven science fiction and scientific inquiry alike for generations. For now, we haven't found definitive evidence of life elsewhere, but the possibility feels closer than ever, given how many hospitable realms may exist. Standing under the night sky now, when you look up at the myriad stars, it's thrilling to think that almost every one of them could be accompanied by planets. Some of those planets might be utterly alien, with crushing atmospheres of sulfuric acid or surfaces of molten rock. Some might be water worlds entirely covered in global oceans, or ice giants with no solid surface at all. And some might be kindred to our own Earth, with blue skies, clouds, and perhaps life thriving under an alien sun. The night no longer feels empty. It is full of destinations, like countless tiny lanterns, each illuminating its own system of worlds. These other worlds have transformed our cosmic perspective. We no longer view our solar system as an isolated oasis in a void, but rather as one garden among myriad others. As our telescopes and space probes grow more advanced, we may eventually be able to observe some of these distant planets directly, to see the pale blue dot of an Earth-like world circling a distant star, or the ruddy glow of a desert planet, or the gleam of sunlight off the clouds of a giant. We might detect seasonal changes in their atmospheres, or the colours of alien forests, or perhaps something beyond our imagination entirely. Each bit of information will enrich our understanding. For now, our exploration of exoplanets is largely indirect, through distant observations and patient inference. Yet, think how far we've come in just a few decades, from wondering if other planetary systems existed at all, to knowing that the night sky is full of them. Each new discovery whispers to us that the cosmos is more diverse and more wonderful than we had imagined, and each of those whispers beckons us further. Yet, as we consider these myriad planets scattered around distant suns, we must remember that they, like our own Earth, owe their existence to the stars they orbit. Planets are born in the disks of gas and dust that surround young stars. They are the byproducts of star formation, children of the same nebula that gives birth to the star itself. To truly understand these other worlds, we must understand how their parent stars live and die, and how the cosmic cycle of creation and destruction sets the stage for planets to emerge. So let us turn now to the lives of the stars themselves, from their birth in clouds of stardust to their often fiery demise. For the story of the stars is ultimately the story of how everything in the cosmos is connected. Drift now into one of the great stellar nurseries of the galaxy, vast, dark clouds of gas and dust where new stars are born. In the silence of these lightless regions, deep within a nebula, gravity is gently at work. Here and there, denser knots of material begin to draw in surrounding gas, their mass growing, their cores slowly compressing and heating. For thousands upon thousands of years, these embryonic stars gather matter in their hidden cradles. If we could speed up time, we would see the cloud begin to glow as pockets of warm gas light up. In one corner of the nebula, a new star ignites, a brilliant pinprick of light piercing the veil of dust. What was once an invisible clump now shines as a protostar, announcing its birth with a faint stellar cry. As the surrounding gas is blown away by stellar winds and intense radiation, the newborn star emerges from its cocoon. It takes its place among the stars of the galaxy, a fresh spark in the darkness. Often, A swirling disk of leftover gas and dust encircles the young star. In that disk, bits of matter collide and clump together, gradually building up into planets, moons, and asteroids, the seeds of a new solar system. Thus, the birth of a star is usually accompanied by the birth of worlds. Our own sun and earth began their journey this way, as part of a collapsing cloud of stardust billions of years ago. Once a star is born, it settles into the long, stable phase of life called the main sequence. This is the star's adulthood, a period of relative equilibrium that can last for millions or billions of years. In its core, a steady nuclear fire converts hydrogen into helium, releasing a vast outpouring of energy. The outward pressure from this energy balances the inward pull of gravity, creating an internal stalemate that keeps the star stable. Our Sun, for example, has been in this steady phase for about 4.5 billion years, and it's only about halfway through its main sequence lifetime. During the main sequence, a star's light and heat remain fairly constant. The sun that shines down on us today is much the same as the sun that shone on the first humans, and it will remain much the same for countless generations to come. But like every living thing, a star's youthful energy is finite. When a star similar in mass to our sun finally exhausts the hydrogen fuel in its core, the delicate balance begins to tip. With less fusion pushing outward from the core, gravity gains the upper hand and the core starts to shrink. As it contracts, it heats up even more, and that intense heat causes the star's outer layers to swell dramatically. The star balloons to many times its original size, becoming what we call a red giant. One day, in the far future, our sun will undergo this transformation. It will expand to perhaps 100 times its current diameter, swallowing Mercury and Venus, and likely scorching Earth to a barren cinder, or even engulfing it. The sun's light will turn reddish and dimmer per square meter, but it will cover a vast portion of our sky. Earth's oceans will boil away, and the sky may take on an eerie copper glow under the bloated sun. Life as we know it would come to an end long before the sun reaches its largest size. It's a daunting fate, but thankfully it lies billions of years in the future, an unimaginably long reprieve by human standards. In the red giant phase, although the star's surface cools and reddens, the core is now an oven of tremendous heat. New fusion reactions ignite in layers around the core. For example, helium that had accumulated in the core begins to fuse into carbon. For a star like the Sun, this helium-burning phase is relatively short, lasting only a few tens of millions of years. The star becomes unstable, pulsating and shedding some mass. In the final stages, it cannot hold on to its swollen outer layers. Those outer layers drift off into space, pushed by pulsations and stellar winds, forming an expanding luminous cloud called a planetary nebula. Early astronomers who first observed these objects in their telescopes thought they looked like planetary disks, hence the name. But in reality, a planetary nebula has nothing to do with planets. It's the glowing shroud of gas cast off by a dying star, often taking on beautiful and ghostly shapes. Some look like delicate rings or loops. The Ring Nebula in the constellation Lyra, for instance, is a tiny smoke ring of gas visible in a backyard telescope, all that remains of a star that once was similar to our Sun. At the center of a planetary nebula, you can often find a small, hot star. That is the remains of the original star's core. After the Sun has shed its outer layers, what remains at its heart is an exposed, fiercely hot core about the size of the Earth. This is a white dwarf. It contains roughly the mass of the Sun compressed into a volume 1,000,000 times smaller, an object so dense that a teaspoon of its material would weigh as much as an elephant. No fusion burns in the white dwarf's interior. It is supported by quantum pressure and will gradually cool over billions of years. When it first forms, it shines white-blue with leftover heat. Over time, it will fade to orange, red, and eventually become a cold, dark cinder, a hypothetical black dwarf, though the universe is not old enough for any black dwarfs to exist yet. The planetary nebula surrounding it, meanwhile, will disperse into space, its constituent gases perhaps later swept up into new star-forming clouds elsewhere. Thus ends the life of a sun-like star, not with a bang, but with a gentle release of its outer self to enrich the cosmos, leaving behind a dense stellar ember. That is the gentle death of a modest star. But not all stars go so quietly into the night. For the giants among stars, those perhaps 10 times the sun's mass or more, the final act is far more violent. Massive stars live fast and die young. A star, say 20 times the sun's mass, might burn through its hydrogen in only a few million years, a blink of an eye compared to the sun's 10 billion year lifespan. As it nears the end of its life, it expands into a supergiant and begins fusing heavier and heavier elements in a desperate bid to sustain itself. Hydrogen fusion in the core gives way to helium fusion, then to carbon, to neon, to oxygen, to silicon. Layer after layer of fusion shells, like an onion. Each stage burns faster than the last. By the time a massive star is fusing silicon into iron in its core, that final fuel lasts only days. The reason is, iron fusion yields no energy. It's a dead end. So once an iron core forms, the star is living on borrowed time measured in moments. When the core of a massive star fills up with iron and can no longer produce energy, the balance maintaining the star's stability collapses. The iron core, about the size of Earth, but more massive than the Sun, succumbs to gravity and implodes in a fraction of a second. The core's atoms are crushed together so tightly that electrons and protons combine into neutrons, and the core itself becomes a super-dense ball of neutrons. This collapse releases an enormous burst of energy. In that brief instant, the infalling outer layers hit this rebounding core and are blasted outward in a titanic explosion, a supernova. The star's outer layers are expelled at a few % of the speed of light, and the energy released can outshine a whole galaxy for a short time. A single supernova can radiate as much energy in a week as our sun will in its entire 10 billion year lifetime. If such a supernova happened in our cosmic neighborhood, it would be an incredible sight. For a few weeks or months, a new star would rival the moon in brightness, casting shadows at night, and perhaps even visible in the daytime sky. In fact, humans have observed such events long ago, without knowing what they were. The guest star of 1054 AD was one. So was another in 1604, observed by Johannes Kepler, a star that mysteriously appeared and slowly faded. These were supernovae in our galaxy. The 1054 supernova left behind the Crab Nebula. Kepler's supernova remnant is a faint expanding shell visible with telescopes. In more recent times, in 1987, a supernova exploded in a nearby companion galaxy, the Large Magellanic Cloud, and was visible to the naked eye from the southern hemisphere, the brightest supernova seen since the invention of the telescope. And there are stars in our own Milky Way that could go supernova in the geological near future. Betelgeuse, our red supergiant friend in Orion, is one candidate. It's expected to explode sometime in the next 100,000 years, a mere eye blink by cosmic standards. When it does, for a time it may shine as bright as the full moon, visible even in daytime, though fortunately it's far enough, about 600 light-years, that it will not harm life on Earth. Future generations might witness that spectacular event, seeing Orion briefly boast a second dazzling star where once was a red dot. What remains after a massive star goes supernova. The debris from the explosion, the star's outer layers, hurtle into space, creating an expanding nebula that glows with the energy of radioactive elements produced in the blast. The Crab Nebula is one such remnant, its tendrils of gas marking where a star once shone. These supernova remnants enrich the galaxy with heavy elements: gold, silver, iodine, uranium, elements that a star can only forge in the sudden fury of a supernova. Those elements will drift through space, mixing into future gas clouds that may one day form new stars and planets. And at the center of the chaos lies the former star's core, now transformed. If the star was moderately massive, say up to 20 or so solar masses, the core's collapse is halted by the quantum pressure of neutrons, leaving behind a neutron star, an ultra-dense object about the size of a city. A teaspoon of neutron star material would outweigh a mountain. Some neutron stars spin rapidly and emit beams of radiation. We observe those as pulsars, blinking on and off like cosmic lighthouses. The Crab Nebula, for instance, has a pulsar at its heart, the crushed core of the star that exploded. On the other hand, if the original star was truly colossal, much more than 20 solar masses, even the neutron star state cannot support the core against gravity. The core continues to collapse until it becomes a black hole, a point of almost infinite density, surrounded by an event horizon from which nothing, not even light, can escape. This newborn black hole, quiet and dark, is the final remnant of a once brilliant star. It may seem like an exclamation point on the star's story, a mysterious endpoint, but in a sense, even that is not truly the end. Yet, in the grand scheme, even the death of a star is not an end so much as a transformation. The matter expelled by dying stars does not vanish. It becomes the raw material for new cosmic creations. The gas and dust blown into space by a red giant or hurled outward by a supernova carry all the diverse elements that the star forged in its lifetime. Those elements, carbon, nitrogen, oxygen, silicon, iron, and so on, will become part of the cold molecular clouds that eventually give birth to the next generation of stars and planets. In fact, every ingredient of our Earth and our bodies, beyond the simplest gas, hydrogen, was cooked up in stars and scattered across space by stellar winds or stellar explosions. Think of it. Long before our sun existed, there had to be other suns that lived and died, enriching the galaxy with heavy elements. Our sun was born from a nebula seeded with those elements. The iron in your blood was once part of a star that ended its life in a supernova. The calcium in your teeth and bones was fused in the heart of a massive star eons ago. In a very literal way, we are starborn. The universe recycled itself to make us. As a poet might put it, we are the universe made conscious, stardust that can contemplate the stars. Stars, then, are not eternal, unchanging beacons fixed in the firmament. They are living cosmic entities of a sort, with lifespans and life cycles. They have fiery births, long stable midlives, and varied spectacular ends. In their death, they fertilize space with new ingredients. Nothing in the cosmos is wasted. Even the ashes of dead stars become the building blocks of new stars, new planets, and possibly new living beings. Our sun is just one of hundreds of billions of stars in our galaxy, each at its own stage of this grand cycle of stellar life and death. When you look up at the night sky, among those points of light are stars being born in distant nebulas, stars in the full bloom of youth, stars in their sedate middle age, and stars nearing their final breaths. And faintly visible, often only through telescopes, are the ethereal remnants of stars that have died, the silent nebulae and tiny degenerate stars left behind. The sky is like a vast family album of stars, capturing every phase of their existence. Having followed the journey of a star from its beginning to its end, we start to see how intimately connected everything in the cosmos is. The life of a star is linked to the evolution of galaxies and to the existence of planets and life. The story of stars is a story of constant change and renewal, a great cosmic recycling program that has been running for more than 13 billion years and continues to this day across the universe. All of this unfolds within our galactic home, the Milky Way. Our galaxy is the grand stage on which the drama of stellar birth and death plays out among uncountable stars. To truly appreciate these processes, we should step back and consider the environment in which they occur, the vast city of stars that is our galaxy. So now, our journey takes us into the Milky Way itself, the great river of light in the sky, the island of stars we call home. On a clear, dark night, when you look up from a place far from city lights, you might notice a pale, milky band stretching across the sky. It appears as if someone took a brush and painted a faint streak of luminous cloud overhead. This is the Milky Way, our home galaxy seen from within. To the naked eye, it looks like a continuous misty glow, but that soft luminosity is actually the combined light of billions of distant stars, too far and too faint to distinguish individually. It arches across the heavens, a river of diffuse light flowing from horizon to horizon. Throughout human history, that ghostly band has inspired wonder and storytelling. Many cultures saw it as a pathway or a bridge in the sky. In ancient China, it was called the Silver River, a celestial stream separating two lovers, the cowherd and the weaver girl, represented by the stars Altair and Vega, who could only meet once a year when a bridge of magpies formed across the river. In southern Africa, some called it the backbone of night, imagining it as the spine that holds up the sky. The ancient Greeks told of it as milk spilled from the breast of the goddess Hera, hence the term Milky Way. To the Romans it was Via Lactea, the road of milk. Others have called it the path of the birds, the straw thief's way, the road of souls. Nearly every culture found a name and meaning for that ethereal band, reflecting its prominence in the night sky and its impact on the human imagination. For astronomers, the Milky Way long posed a mystery. What was this band of light? Some early thinkers, like the 18th century philosopher Immanuel Kant, speculated that it might be a disk of countless stars, an island universe, and that the nebulae seen in telescopes might be other galaxies far away. He turned out to be correct, but proof would have to wait. Not until the early 20th century did we assemble a clear picture of our galaxy. By carefully mapping the positions of stars and clusters, astronomers realized that the Milky Way is indeed a flattened disk of stars, and that the sun is not at the center of things, but rather out towards the side. They estimated the Milky Way's span to be on the order of 100,000 light-years across, an enormous expanse by any measure. Our Sun, with its family of planets, resides in this galactic disk. We are about 26,000 light-years from the Milky Way's center, roughly halfway between the core and the edge. If we could view our galaxy from far above, we'd see a broad, flat spiral, like a giant frisbee made of stars, with a central bulge of densely packed older stars. Our Sun would be just one tiny point of light among hundreds of billions of others, situated in a minor spiral arm or spur known as the Orion Arm or Orion Spur. From our vantage point inside the disk, we perceive the concentrated starlight of the disk as that milky band encircling us. When we look toward the constellation Sagittarius on a summer night from the northern hemisphere, we are looking toward the galaxy's center. That's why the Milky Way seems especially rich and bright in that direction. Millions of stars crowd together in the central regions, though interstellar dust hides the true hub from visible light. In contrast, if you look perpendicular to the band of the Milky Way, say toward the North Star Polaris or the constellations of spring, you are looking out of the plane of the galaxy into clearer, emptier space, and so the Milky Way band appears fainter or even missing in those directions. The dark patches that you can see within the Milky Way, rifts where the starry glow is interrupted, are not cosmic voids, but rather huge clouds of dust. These dust clouds, the remains of previous generations of stars and the raw material for future ones, block the light of the stars behind them. To the eye they appear as irregular dark gaps, but telescopes that can see other wavelengths, like infrared, reveal them as structures threading through the galaxy's spiral arms. At the heart of the Milky Way lies a dynamic and tumultuous region. We can't see it with optical telescopes because of intervening dust, but with radio and infrared observations, we peer into the galactic center. There we find a dense swarm of stars orbiting something we cannot see directly, something very massive. Stars at the center whip around at astonishing speeds, some completing orbits in just a decade or so, whereas our Sun takes 230 million years to orbit the galaxy. By tracking these orbits, astronomers have deduced that a supermassive black hole resides at the Milky Way's core. We call it Sagittarius A. It contains the mass of about 4 million suns, crammed into a space smaller than our solar system. Occasionally, when gas clouds or stars stray too close, the black hole's gravity pulls some of that material in. As the material spirals into the black hole, it heats up and emits flares of X-rays and radio waves. We normally don't notice this black hole. To us, the center of the galaxy just looks like a rich star field with no obvious central object. But it's there, the dark anchor of our galactic nucleus. The Milky Way is not just a flat disk of stars with a black hole at the center. It has a central bulge, a roundish concentration of older stars in the middle, like a yolk in the fried egg structure of the galaxy. It also has an extended halo, a sphere of tenuous star clusters and dark matter that envelops the whole disk. Scattered in this halo are globular clusters, which are densely packed, spherical collections of ancient stars. These globular clusters, perhaps 150 or so of them, orbit the center of the galaxy in all directions, like a swarm of bees around a hive. They contain some of the oldest stars known, fossils from the early days of our galaxy over 12 billion years ago. It was by mapping the distribution of globular clusters that the astronomer Harlow Shapley, in 1918, determined that the Milky Way's center lies in Sagittarius, not near Earth, as previously assumed, and that the galaxy was much larger than we had thought. The halo of the galaxy also harbors something we can't see directly: dark matter. This mysterious substance does not emit or absorb light, so it's invisible to our instruments. But its gravity affects the motions of stars and gas. Stars in the outskirts of the Milky Way orbit faster than they would if only visible matter were present, which is best explained by a large halo of dark matter enveloping the galaxy. In effect, the Milky Way is like an iceberg. The stars, gas, and dust we see are just the tip, while the bulk of its mass, the dark matter, is hidden below the surface of visibility. What exactly dark matter is remains one of the great, unanswered questions in astronomy. A reminder that even in our own galaxy, there are fundamental mysteries. Within the luminous disk of the Milky Way, especially along the spiral arms, the story of stellar life and death continues in full swing. Giant molecular clouds, massive assemblies of gas and dust, serve as stellar nurseries. We spoke of these earlier. Within them, new stars ignite and light up the surrounding nebulae. The Orion Nebula, visible below Orion's belt, is one such stellar nursery, where hundreds of new stars are forming. Along the spiral arms, clusters of young blue stars trace out the pattern of the arms. Because these hot stars don't live long, and thus never drift far from their birthplaces. Scattered among them are the remnants of stars that have died, supernova remnants, planetary nebulae, expanding shells of gas. The spiral arms themselves are like traffic jams in the galaxy's disk, cosmic density waves that sweep through, triggering bursts of star formation as they compress the gas clouds. Our Sun currently finds itself between two major spiral arms in a smaller feature, but it too participates in the general rotation of the galaxy. Indeed, the Sun is on a great journey of its own. It orbits the center of the Milky Way roughly once every 230 million years. This means the last time the Sun was in its current position around the galaxy, the most advanced life on Earth were the early dinosaurs. And when the Sun completes its next lap, who knows what life forms might witness that far future era. As our solar system circles the galactic center, it bobbles slightly up and down through the plane of the disk, like a horse on a carousel, passing through regions of varying stellar density. Some scientists have even speculated that these passages through crowded spiral arms might have influenced life on Earth by disturbing comets or increasing supernova nearby. But this remains an open topic of research. The sheer scale of the Milky Way can be hard to fathom. Hundreds of billions of stars, vast interstellar clouds, tens or hundreds of light years across, clusters and nebulae scattered like blossoms. If we tried to count the stars in the galaxy at a rate of 1 per second, we wouldn't live long enough to finish the job. And yet, from our vantage point on Earth, we see the Milky Way as just a hazy band. Here's a mind-bending analogy. If the entire solar system out to Neptune were shrunk to the size of a coffee cup, the Milky Way would still span several continents. In other words, the galaxy is overwhelmingly vast compared to the spaces we're familiar with. For a long time, people thought the Milky Way might be the entirety of the universe. Those faint, fuzzy nebulae seen in early telescopes were assumed to be nearby gas clouds or star clusters within our galaxy. The idea that they could be separate galaxies like our own was hotly debated. This debate was settled in the 1920s when Edwin Hubble and others around the same time measured distances to certain variable stars in the Great Andromeda Nebula. He found that Andromeda was far, far beyond the Milky Way, millions of light years away, too distant to be part of our galaxy. It wasn't a small nebula. It was an enormous galaxy of its own, comparable in size to the Milky Way. Astronomers suddenly realized that the universe is composed of many galaxies, not just one. The Milky Way, as immense as it is is just one of countless island universes adrift in space. Today, we know the Milky Way is one galaxy among a vast multitude. It's a big galaxy, certainly, a majestic barred spiral with its spiral arms and orderly rotation. But it's by no means unique or the largest. It shares the universe with galaxies of all shapes and sizes. Our Milky Way is part of a small cluster of galaxies called the Local Group. This group contains our galaxy, the Andromeda Galaxy, our slightly larger neighbour, the Triangulum Galaxy, a smaller spiral, and dozens of dwarf galaxies that are much smaller. The Milky Way and Andromeda dominate the Local Group, each with their system of satellite galaxies. Andromeda, located about 2.5 million light-years from us, can actually be seen as a faint smudge in the constellation Andromeda on a very dark night. It's the most distant thing visible to the naked eye. Interestingly, the Milky Way and Andromeda are moving toward each other. In about 4 billion years, these two great galaxies will begin to merge in a slow gravitational dance that will last another few billion years. The result will likely be a large elliptical galaxy. The spirals will be gone, their stars mixed into a more amorphous cloud. Future Earth, if Earth still exists then, would see an entirely different night sky during that merger, with new patterns of stars and perhaps huge glowing tidal tails arcing across the heavens as the galaxies interact. Orbiting our Milky Way are several dwarf galaxies, essentially miniature galaxies with only a few billion stars or less. Two of these, the Large and Small Magellanic Clouds, are visible from the southern hemisphere as fuzzy patches of light. They look like detached pieces of the Milky Way, and indeed, they are in orbit around it, bound by gravity. They're being slowly disrupted by our galaxy's pull. Eventually, they may be torn apart, and their stars added to the Milky Way. In fact, astronomers have found streams of stars in our galaxy's halo that appear to be the remnants of small galaxies devoured in the past. The Milky Way has grown over billions of years by cannibalizing smaller systems. Even now, it's dining on at least one small dwarf galaxy, pulling it apart. So galaxies are not isolated static islands. They interact, collide, and merge, especially within clusters, shaping each other's evolution. Standing under the night sky and contemplating that milky band, it's awe-inspiring to realize that this hazy glow is the collective light of our entire galactic metropolis. Every tiny patch of that band, viewed with a telescope, resolves into countless stars. And around many of those stars are planets. And on at least one of those planets, creatures evolved who can look back and marvel at it all. When we send spacecraft beyond our solar system, as we have with the Voyager and Pioneer probes, they are still barely a stone's throw into the outskirts of the Milky Way. It would take those probes tens of thousands of years just to travel a fraction of the distance to the nearest stars. To cross the galaxy would take millions. For the foreseeable future, our reach is limited to our cosmic neighborhood. So we study our galaxy mostly from within, piecing together its structure bit by bit, somewhat like a person trying to deduce the shape of a forest while being deep inside it. Yet, piece it together we have. We have mapped the spiral arms using radio telescopes to trace hydrogen gas. We have measured the galactic rotation. We've even taken a kind of family portrait of the Milky Way by observing similar galaxies from the outside and inferring that our own likely looks much like a splendid spiral we might see in the sky, if only we could get above the galactic plane. As our knowledge has grown, so has our appreciation of the Milky Way's place in the cosmos. We once thought it was the universe. Now we know it is one of an uncountable multitude. The Milky Way is our home, our immediate cosmic neighborhood, and it will always have special significance to us. But beyond our galaxy's edge lies the great ocean of other galaxies, each with its own stars, its own possibilities. Beyond the Milky Way, in every direction we turn our telescopes, there are galaxies upon galaxies, immense assemblies of stars, gas, dust, and dark matter, each separated from the next by vast gulfs of nearly empty space. It is almost beyond comprehension. The observable universe contains hundreds of billions, perhaps trillions of galaxies. Each galaxy, like our own, is an island of light in the cosmic ocean, containing on average tens or hundreds of billions of stars. When we peer into the deep sky with powerful instruments, we see these galaxies scattered across space like far-flung cities in the darkness. Even a patch of sky that appears blank and black to our eyes is revealed, under long exposure, to be filled with faint galaxies lurking at the edge of detectability. One of the most humbling images ever captured was the Hubble Deep Field. In the 1990s, astronomers selected a tiny, seemingly empty spot in the sky, an area no bigger than a grain of sand held at arm's length, and pointed the Hubble Space Telescope there for about 10 days, letting light slowly trickle in. What returned was a picture for the ages, a deep window into the universe's distant past, showing over 3,000 galaxies in that minuscule speck of sky. Every smudge or point of light in the image, save for a couple of foreground stars, was an entire galaxy. Some showed majestic spiral shapes, others looked like pale ellipses, and many were just faint, featureless blotches. Galaxies so distant their structures could not be resolved, their light having travelled billions upon billions of years to reach us. If such a tiny patch of sky holds thousands of galaxies, imagine how many galaxies fill the entire sky. The deep field gave a visceral sense of the enormity of the cosmos, that in all directions, wherever we look, the universe stretches on, populated with uncountable worlds of stars. Galaxies, like stars, come in different varieties. There are graceful spiral galaxies, like the Milky Way or the Andromeda Galaxy, with curving arms spinning out from a central bulge. These tend to have lots of gas and dust in their disks and active star formation in their spiral arms, which is why their arms look bluish from the light of young stars, sprinkled with pinkish nebulae, glowing clouds of ionized hydrogen around newborn stars. Andromeda, our nearest large neighbor, is a spiral much like our own, and in dark skies you can just make out its elongated glow. There are also barred spirals, where a straight bar of stars cuts through the central region with arms spiraling off the ends. Our Milky Way is thought to have such a bar structure in its core. Another major class of galaxies are the ellipticals. These range from nearly spherical to highly elongated, football-like shapes. Elliptical galaxies have a smooth, featureless light profile, generally a golden color, owing to their stars being older and more evolved, and thus redder. They contain relatively little cold gas or dust, which means new star formation has largely ceased within them. Instead, they are populated by billions of aging stars and often a significant number of globular clusters. Some ellipticals are small, dwarf ellipticals, perhaps satellites of larger galaxies. Others are absolutely enormous, giant ellipticals that sit in the hearts of galaxy clusters. These giants might span 1 million light-years and hold trillions of stars, often the result of numerous past mergers of smaller galaxies. They are cosmic retirement homes for stars, places where the frenetic star birth of youth is long over, and the galaxies glow with a steady, ancient light. Then there are irregular galaxies, the nonconformists. These have no clear spiral structure or elliptical shape. Many irregulars are small dwarf galaxies that have been distorted by gravitational interactions or simply never formed into a symmetric shape. The large and small Magellanic Clouds orbiting our Milky Way are classic examples of irregular galaxies. They look like amorphous patches of stars and gas, each a fraction of our galaxy's size. The Magellanic Clouds are currently interacting with the Milky Way and likely with each other, which explains their distorted shapes. Irregular galaxies often have abundant gas and ongoing star formation, sometimes ignited by encounters with larger neighbours. Just as stars tend to gather in clusters and galaxies in groups, galaxies themselves congregate on larger scales. The universe has a hierarchy. Our Milky Way is part of the local group, which contains a few dozen galaxies in a region a few million light-years across. The local group, in turn, is on the outskirts of the Virgo cluster, a much larger cluster of galaxies roughly 50 million light-years away from us. The Virgo cluster is an enormous concentration of over 1,000 galaxies bound together by gravity, and it is the nearest big galaxy cluster to our own group. Looking even further, galaxy clusters bunch together into superclusters, forming immense chains and walls. The Virgo cluster is part of the Virgo supercluster, also sometimes called the local supercluster, which is a broad structure tens of millions of light-years across, containing many groups and clusters, including Virgo and our local group. And even those superclusters form patterns. Through large-scale surveys, we've found that superclusters are arranged in filaments and sheets surrounding huge voids where few galaxies dwell. The overall picture is like a vast cosmic web or sponge, filaments and walls of galaxies interweaving, with bubble-like voids in between. Our home supercluster, in fact, has been subsumed into an even larger concept called Laniakea, a Hawaiian word meaning immeasurable heaven, which encompasses a gargantuan region of the cosmic web that our Milky Way is just a tiny part of. When we observe galaxies at extreme distances, we are also looking deep into the past. A galaxy seen 10 billion light-years away is being observed as it was 10 billion years ago, when it was perhaps in its youthful stage. Thanks to telescopes like Hubble and now the James Webb Space Telescope, we have peered at some of the earliest galaxies that formed in the universe. These early galaxies tend to be smaller, more irregular clumps. They often look like little fragments or seeds of what will later become full-sized galaxies. They are sites of frantic star formation, blazing brightly with massive young stars. Over billions of years, such proto-galaxies merged and merged again, building up larger galaxies, a process that continues to this day. Our own Milky Way likely began as a few smaller systems that coalesced, and it has been growing ever since by accreting gas and swallowing dwarfs. And in the future, the dance continues. In about 4 billion years, the Milky Way and Andromeda will begin to merge. It's hard to predict exactly what the resulting galaxy will look like, likely a giant elliptical after things settle down. But during the merger, the night sky from Earth, if Earth is still around, will be spectacular. Andromeda will loom larger and larger, eventually stretching across the sky. New star formation might light up as gas clouds collide. Over a few billion years, the two spiral structures will tangle and dissipate, flinging stars into looping tidal streams. By the end of the merger, perhaps 6 or 7 billion years from now, the Sun will reside in a very different galaxy than the one it was born in, a sort of cosmic rebirth for our stellar population. Galactic interactions like this are dramatic, but remember that stars within colliding galaxies mostly do not hit each other. The distances between stars are so vast that when two galaxies merge, their stars mingle like interleaving two decks of cards. The real action is in the gravitational effects. Whole systems of stars get thrown into new orbits, and huge clouds of gas slam into each other. Those gas collisions can trigger bursts of starbirth, sometimes called starburst galaxies result, where new stars are forming at a furious rate, colouring the galaxy with the blue light of massive young stars and the glowing red of hydrogen nebulas. Over time, much of the gas may be used up or ejected, and the star formation slows back down. At the cores of nearly all large galaxies lie supermassive black holes, as we noted with our own Sagittarius A. Other galaxies have them too, and some are far larger than ours, billions of solar masses. These cosmic heavyweights can profoundly influence their host galaxies, especially when they're actively feeding. In some galaxies, especially in the young universe or during mergers, gas falls toward the central black hole and forms a superheated accretion disk. This disk can blaze across the electromagnetic spectrum, powered by gravity, converting matter into energy with extreme efficiency. The result is what we call an active galactic nucleus, AGN. If the AGN is exceptionally bright, we call it a quasar. Quasars were a great mystery when first discovered in the 1960s. They looked like star-like points, but with incredibly high redshifts, meaning they were very distant and immensely luminous. We now understand that a quasar is basically a galaxy's central black hole in feeding mode, shining so brightly that it drowns out the rest of the galaxy's light. Quasars are often found in the early universe, when galaxies were forming and merging more frequently, providing ample fuel to their black holes. Some shoot out enormous jets of particles that extend thousands of light years, marking their presence like beacons. Observing quasars is like watching cosmic bonfires from a time when the universe was young and rambunctious. In the 1920s, after establishing that galaxies are distant islands in their own right, Edwin Hubble made another monumental discovery. He found that the light from most galaxies is redshifted. That is, the spectral lines of their stars are shifted toward longer, redder wavelengths compared to where they would be if the galaxy were at rest. This redshift suggested the galaxies were moving away from us. Furthermore, the farther a galaxy was, as determined by certain standard candles like Cepheid variable stars, the greater its redshift. In other words, more distant galaxies appeared to recede faster. This relation, now known as Hubble's law, is best explained by the expansion of the universe. Space itself is stretching in all directions, carrying galaxies with it. No galaxy is at the center of the expansion. From any galaxy's viewpoint, others appear to be rushing away. If the universe is expanding now, it implies that in the past, everything was closer together. Wind back the cosmic clock about 13.8 billion years, and you reach a state where the universe was extremely hot, dense, and much smaller. The time of the Big Bang, the origin of the expanding universe. The galaxies themselves would not yet have existed in those very early moments. They coalesced hundreds of millions of years later. But they carry in their motions the evidence of that explosive origin. Today, we also detect an intriguing twist. The expansion of the universe is accelerating. Distant supernova studies in the late 1990s revealed that galaxies are receding faster and faster over time, as if some mysterious repulsive force is pushing the cosmos outward. We call that force dark energy, and it remains one of the biggest puzzles in cosmology. It's as if, on the scale of the entire universe, there is an inbuilt tendency for expansion to speed up, overcoming gravity at the largest distances. Billions of years from now, distant galaxies will be rushing away so fast that their light will become undetectable to us, leaving each galaxy or group of galaxies more isolated in the darkness. So, the galaxies beyond our Milky Way are not just static objects. Their collective behavior tells us about the universe's past and future. They allowed us to discover that the cosmos is expanding and gave us clues about the Big Bang. Their distribution and motions hint at the presence of dark matter. As galaxies rotate and move within clusters, we see gravitational effects that require more mass than we can see. And the accelerating expansion revealed by distant galaxies introduced the concept of dark energy. In this way, by studying other galaxies, we've begun to unravel the grand story of the universe. As we survey the heavens filled with galaxies, we realize that these islands of light tell the story of the cosmos across time. In the faint glow of the most distant galaxies, we are glimpsing the universe as a toddler. Galaxies just starting to form, stars just starting to shine. In the giant elliptical galaxies full of old stars, we see cosmic maturity and the product of many mergers. In the grand design spirals, we see a mix of ongoing creation and ancient structure. The cosmic web of galaxies and voids maps the subtle imprints of the universe's earliest moments, tiny density differences in the early universe that grew into the large-scale structure we see now. Each galaxy is like a chapter in an epic. Some chapters are the quiet development of stars and planets. Others are dramatic collisions. Others are the shining pageantry of a quasar. Standing back and taking it all in, we are confronted with the immensity of creation and the unity of its fundamental ingredients. The same physics governs a star here in our galaxy and a star in a galaxy billions of light years away. The same types of atoms, forged in stars, drift through intergalactic space and end up in new galaxies. We truly are connected to the farthest reaches of the universe by these threads of common history and composition. Our little planet orbits an ordinary star in the suburbs of one galaxy. Yet from that humble vantage point, using ingenuity and curiosity, we have managed to explore out to the cosmic horizon. We've sent our awareness to the edge of the observable universe, decoding the faint light that reaches us after billions of years in transit. The journey from our familiar Earth to the realms of distant galaxies is perhaps the greatest intellectual adventure our species has ever undertaken. In just a few centuries, we've gone from a static, Earth-centered cosmos, a few thousand years old, to a dynamic, expanding universe, 13.8 billion years in the making, containing structures of staggering scale. With each step outward, from Earth to the solar system, to the stars of the Milky Way, to the galaxies beyond, our perspective has been profoundly reshaped. We have learned that the Earth is not the center of the solar system, the Sun is not the center of the galaxy, and the Milky Way is not the center of the universe. We inhabit one planet among many, one star among many, one galaxy among many. Yet, far from making us insignificant, this realization fills many of us with awe and reverence for the cosmos. We are part of something vast and magnificent. We are a way for the universe to know itself, having evolved out of the very stars and galaxies we study. We ponder whether somewhere out there, perhaps in one of those billions of galaxies, other beings are also looking up and asking similar questions. Are we alone? Or is the universe teeming with life, spread among the galaxies, like blossoms in spring? We do not know. Not yet. But the possibility adds another layer of wonder to our cosmic view. The more we learn, the more we understand that our voyage of discovery is far from over. With every new telescope, every new mission, we uncover new mysteries. What lies beyond the edge of the observable universe? What is the ultimate fate of the cosmos? Will the galaxies drift apart until none are visible? Will everything collapse back? Or something even stranger? How did the very first galaxies form? And what seeds gave birth to them? Each answer we find tends to spark new questions in an endless cycle of curiosity. For now, we pause on the shores of the cosmic ocean, gazing out at the innumerable galaxies glimmering in its depths. We feel humbled by the scale of it all, yet inspired that we can even contemplate it. The cosmos is vast and full of marvels beyond imagining, from the tiniest mote of cosmic dust to the grandest galactic cluster. And here we stand, tiny creatures on a small world, but with minds able to map the universe and hearts able to feel its beauty. Our journey through space and time is far from finished. As long as we continue to look up in wonder, the story of exploration goes on, an endless quest to understand and to celebrate the marvelous cosmos we inhabit. For countless ages, human beings have gazed into the night sky and wondered how all of this came to be. Every culture imagined its own beginning. In some myths, the universe hatched from a cosmic egg. In others, a word from a deity conjured light from darkness. Ancient storytellers spoke of chaos giving birth to order, of gods and giants forging the world from nothingness. These tales tried to capture a truth that seemed beyond reach. Yet the true origin of our cosmos, as best as we understand it today, is more wondrous and mysterious than any story ever told. In the beginning, nearly 14 billion years ago, there was darkness. No stars, no galaxies, not even space or time as we know them. All that existed was a single point of infinite potential, a seed of everything to come. In an instant, this seed burst into existence, unleashing the Big Bang. Space itself unfurled faster than a thought, carrying energy and matter outward at a fantastic rate. In a fraction of a second, the universe swelled from microscopic to cosmic proportions, an unimaginable expansion we call cosmic inflation. It was not an explosion in space, it was an explosion of space itself. Time had begun, and with it came a storm of creation. In the first fleeting moments, the newborn universe was incredibly hot and dense, a glowing fog of particles and light. It expanded and cooled with astonishing speed. In fact, more change happened in the universe's first second than in all the billions of years since. All the forces of nature we know, gravity, electromagnetism, the strong and weak nuclear forces, were once unified in that primordial fire, and then began to separate as the universe grew. Energy congealed into matter. Tiny particles flickered into being. Matter and antimatter pairs appeared and annihilated each other in flashes of light, but a small excess of matter survived. In this cosmic furnace, the simplest elements took shape. Protons and neutrons clustered into the first atomic nuclei of hydrogen and helium within minutes. The universe was just a baby, but it was already busy creating the basic ingredients of everything that would one day exist. As time flowed on, and the universe kept expanding, as it continues to expand even now, the primordial fireball began to cool. By about 380,000 years after the Big Bang, a blink of an eye in cosmic time. The universe had cooled enough for electrons to settle into orbits around nuclei, forming the first atoms. At last, light was free to travel through space. Before then, light had been trapped, bouncing endlessly in the opaque plasma of the young cosmos. But now the universe was transparent and filled with a soft glow in every direction. This gentle afterglow of the Big Bang, the cosmic microwave background, still surrounds us today. It is a faint whisper from the dawn of time, stretched into a cool haze of microwaves by the expansion of space. If our eyes could see it, the entire sky would shimmer with a dim, ancient light, a silent memory of creation. In modern times, scientists have detected this very glow with special instruments, listening to it as a faint background hiss from every corner of the sky. Its discovery confirmed that the universe did indeed have a hot, dense beginning, just as scientists had predicted. In the darkness that followed, there were still no stars, only vast clouds of hydrogen and helium drifting through an expanding void. The cosmos was dark, silent, and cold, awaiting the first spark of starlight. Slowly, gravity began to draw those gas clouds into denser clumps. Over tens of millions of years, some regions grew dense and hot at their cores under gravity's embrace. At last, around 1 to 200 million years after the beginning, the first stars flickered into existence. They ignited in brilliant flashes, piercing the cosmic darkness. Imagine those first stars, monstrously large and fiercely bright, shining blue-white with immense heat. They burned their fuel furiously and lived short, spectacular lives, flooding the young universe with light. With their birth, the cosmic dark ages ended, and the universe began to sparkle with starlight. These early stars were like cosmic alchemists, forging new elements in their blazing hearts: carbon, oxygen, silicon, and many others. They built the raw materials for future planets and for life itself. But such massive stars burn out quickly. After only a few million years, many met their end in colossal supernova explosions. In dying, they blasted their enriched guts, those newly forged elements, into space, scattering the ingredients for planets, oceans, and living creatures yet to come. The deaths of those first stars were violent and brilliant, yet they sowed the seeds of new creation. From the ashes of those ancient suns, new stars, and eventually new worlds would be born. As the eons passed, galaxies began to take shape. Vast cities of stars, guided by gravity's hand. Small proto-galaxies merged into larger ones. Spiral and elliptical galaxies swirled into existence, each a cosmic ecosystem brimming with billions of stars. In our own region of space, the Milky Way galaxy grew into its majestic form, its spiral arms filled with starry neighborhoods. Everywhere, stars were being born and dying, continuing the great cosmic cycle. Generation upon generation of stars enriched the universe with heavier and heavier elements. About 9 billion years after the Big Bang, in one quiet corner of the Milky Way, our sun was born. It emerged from a cloud of gas seeded by countless earlier stars, and around it, planets, including our Earth, coalesced from the leftover dust and gas. On Earth, the stage was set for life to one day emerge, life made from the very elements those ancient stars had created. Every atom in your body, every calcium atom in your bones, every iron atom in your blood, was forged in those stellar furnaces or during their explosive deaths. In a literal sense, we are made of star stuff, bound forever to the cosmos that created us. The story of the universe is our story as well. In this grand cosmic tale, creation and destruction are two sides of the same coin. The death of a star can be as important as its life, often leading to new wonders. One of the most mysterious of these wonders emerges from the final fate of the most massive stars. When a truly giant star dies and collapses under its own gravity, it can leave behind an object so dense, with a pull so strong, that not even light can escape. From the brilliance of the first stars, we now journey into the depths of darkness that followed their death. We venture into the enigmatic realm of black holes, the cosmic abysses born from the ashes of stars. Imagine a star, many times the mass of our sun, reaching the end of its life. In its final moments, the star's core collapses under its own tremendous weight. It shrinks and squeezes inward, tighter and tighter, until all of its mass is packed into an almost infinitely small point. In that instant, a new kind of object is born, a black hole. To ancient sky watchers, the idea of a star collapsing into a lightless abyss would have been unimaginable. Yet here it is, a cosmic reality predicted by modern science. A black hole has no solid surface like a star or planet, only a boundary, the event horizon, marking a point of no return. Once anything falls past that invisible boundary, it can never come back out, not even a beam of light. A black hole is the ultimate cosmic trap. Its gravity is so intense that space itself is pulled inward like a rushing whirlpool. If you drifted too close, you'd be caught in its grip and drawn inexorably toward the center. Near the event horizon, time itself appears to distort. To a distant observer watching you fall, it would seem as if you slow down more and more as you approach the brink, lingering at the edge without ever quite slipping inside. Your image would fade and redden, stretched by gravity's influence on light, until you vanished from view. But from your own perspective, nothing so strange would occur. You would continue to fall, plunging through the event horizon in less than a heartbeat. As you fell, the difference in gravity between your head and your feet would become extreme. It would pull you longer and thinner, stretching your body into a long strand like a piece of spaghetti. Astronomers literally call this spaghettification. In mere moments, you would be torn apart as you journeyed toward the black hole's hidden heart. What lies at that heart, a point of infinite density known as the singularity, is unknown. It is a place where the laws of physics, as we understand them, break down. In the darkness inside a black hole, our knowledge and intuition falter. Black holes come in different sizes. Some are relatively small, formed from the collapsed cores of giant stars. A star 10 times the mass of the Sun might leave behind a black hole just a few miles across, yet containing all that mass in its compact form. Dozens of these stellar mass black holes may be sprinkled throughout each galaxy, including our own, hidden unless they reveal themselves through their gravitational effects on nearby stars or by emitting X-rays as they consume stray gas. On the other end of the scale, there are supermassive black holes weighing millions or even billions of times more than the Sun. Nearly every large galaxy harbors one in its center. Our Milky Way, for example, holds a central black hole about 4 million times the Sun's mass. This dark colossus is quiet now, but its gravity guides the orbits of stars swirling around the galactic core. How such supermassive black holes came to be, whether by the merger of many smaller black holes the collapse of primeval colossal stars, or some other exotic process in the young universe, is still a subject of research and wonder. Despite their name, black holes are not always black. As matter falls toward a black hole, it doesn't simply disappear quietly. The doomed gas and dust spiraling inward form a whirling accretion disk around the black hole, heating up to extreme temperatures and glowing brilliantly before it crosses the horizon. From across space, we can sometimes see this last desperate light. A black hole actively feeding on surrounding material can become the center of a radiant spectacle. In distant young galaxies, supermassive black holes gobbling up gas create quasars, blazing beacons of light that can outshine the billions of normal stars in their host galaxies. It is a striking irony that the darkest objects in the universe can produce some of the brightest lights, as the matter they consume announces its fiery demise. For a long time, black holes existed only as theoretical curiosities in the equations of Einstein's general relativity. Even Einstein himself was hesitant to believe such strange objects could actually form in nature, but over the decades, evidence for black holes slowly mounted. Astronomers noticed that certain stars were orbiting an unseen mass, whipping around in tight, fast orbits, as if held by an invisible gravitational tether. In the 1960s, scientists discovered intense X-ray emissions coming from systems where a visible star seemed to be orbiting an invisible companion, likely a black hole pulling matter from its stellar partner and heating it to an X-ray bright glow. These clues strengthened the case that black holes were real. In recent years, our tools have allowed us to observe black holes in more direct and astonishing ways. In 2015, detectors on Earth felt the gentle tremor of space-time itself when two distant black holes spiraled together and merged. For the first time, we heard a black hole collision, not with our ears, but with exquisitely sensitive instruments picking up gravitational waves, ripples in the fabric of space and time. And then, humanity finally saw the unseeable. Using a network of telescopes spanning the globe, scientists captured the first ever image of a black hole's immediate vicinity. The picture, released in 2019, showed a ring of golden light, hot gas glowing as it swirls near the event horizon, surrounding a circular dark shadow. That dark center was the silhouette of the supermassive black hole in a galaxy far beyond our own. It was a breathtaking confirmation that these extraordinary phenomena are indeed part of our reality. Now, black holes are an accepted part of the cosmic landscape. They are born in the depths of stars and reside in the hearts of galaxies. Our universe is peppered with them, each one a gravitational well from which nothing escapes. Yet even these mighty gravitational prisons may eventually come to an end. Stephen Hawking famously proposed that black holes aren't completely black. They can slowly leak away energy through what is now called Hawking radiation. Over inconceivably long timescales, a black hole can evaporate, particle by particle, until it vanishes. A black hole the mass of our Sun would take far longer than the current age of the universe to evaporate, and supermassive black holes would take even longer. They will be among the last objects to fade out in a distant future. Still, the idea that even the darkest voids can eventually dissolve back into light is a profound one. In the present universe, however, black holes continue to lurk quietly or blaze with power when they feed. They challenge our understanding of physics and inspire awe at their extremes. And remarkably, for all their mystery, black holes account for only a small fraction of the cosmos. There are far larger mysteries filling the universe, things we cannot see at all, not even as a shadow or a silhouette. Beyond the darkness of black holes lies an invisible form of matter that outweighs all the stars, and a mysterious force driving the universe's expansion. Our journey now leads into this unseen realm of dark matter and dark energy, the invisible universe that surrounds and sustains the visible galaxies and stars. In the vast reaches of space, beyond the stars we can see, an even greater portion of the cosmos lies hidden. All the gleaming galaxies, sparkling stars, and luminous nebulae, as immense as they are, form only the tip of the cosmic iceberg. Astronomers have discovered that most of the universe is composed of invisible ingredients, mysterious and unseen. These are known simply as dark matter and dark energy, and together they dominate the cosmos, silently orchestrating the motion of galaxies and the expansion of space itself. The first clue to this invisible universe came from the way galaxies move. In the 1970s, astronomer Vera Rubin and her colleagues measured how fast stars rotate around the centers of spiral galaxies. To their surprise, they found that stars far from a galaxy's center were moving just as quickly as those near the core. According to the known laws of gravity, those outer stars should have been moving more slowly, otherwise the galaxy would fly apart. In fact, by rights, the outer stars should have been flung off into space. But they weren't. The galaxies were intact and spinning with flat rotation curves, meaning the stars' orbital speeds stayed high out to the fringes. That could only make sense if something unseen was providing extra gravity to hold them in. It was as though each galaxy was embedded in a vast halo of mass that we could not see. Astronomers named this unseen mass dark matter. Soon, evidence for dark matter turned up everywhere. Clusters of galaxies, enormous assemblies of hundreds of galaxies, were found to contain far more mass than the visible stars and gas could account for. Something invisible was contributing the majority of the mass. In some places, we observe the light from distant objects being bent and distorted by massive yet unseen foreground concentrations, like a cosmic funhouse mirror. This gravitational lensing effect reveals where mass is distributed in space, and often it maps out structures that have much more mass than what we can see directly. One dramatic example occurred when scientists observed two galaxy clusters colliding with each other. The hot gas in the clusters, which is ordinary matter, slammed together and slowed down, but most of the gravitational mass sailed through the collision unaffected. The implication was clear. The bulk of each cluster's mass was invisible dark matter that does not collide like normal matter. All these lines of evidence point to the same conclusion. The universe has a tremendous amount of matter that is completely dark. What is this dark matter? It's not made of any of the atoms that build familiar things like stars, planets, and people. Those ordinary atoms make up only about 5% of the cosmos. Dark matter seems to be a different kind of particle or substance entirely, one that does not emit or absorb light and barely interacts with anything except through gravity. It surrounds galaxies and permeates clusters in enormous halos, like an invisible scaffolding underlying the structure of the universe. In fact, long before the first stars ignited, dark matter's gravity helped draw together the gas that formed galaxies, tracing out a vast cosmic web. Even today, galaxies cluster along filaments of that cosmic web, following the unseen tug of dark matter. Here on Earth, we are drifting through a sea of dark matter particles without noticing them. Billions may pass through you each moment, and you wouldn't know, because they slip through ordinary matter, almost as if it weren't there. Scientists around the world are trying to unveil this ghostly component of the cosmos. Sensitive detectors, buried deep underground, are listening for the tiniest ping of dark matter particles colliding with atoms. Powerful accelerators, like the Large Hadron Collider, are searching for hints of dark matter in high-energy particle collisions. Space telescopes and galaxy surveys map the distribution of matter to understand where dark matter lurks. Yet so far, the true nature of dark matter remains one of the great unsolved mysteries. If dark matter were the only cosmic mystery, that would be astonishing enough. But the universe had an even bigger surprise. In the late 1990s, astronomers discovered that the expansion of the universe is accelerating. Distant Type Ia supernovae, exploding stars used as standard candles to measure cosmic distances, were observed to be dimmer and thus farther away than expected. It was as if some unknown force had been pushing them, and the space between galaxies farther apart. Instead of slowing down over time, the universe was speeding up. This revelation was a shock to our understanding of cosmology. To explain it, scientists proposed another invisible component of the universe, one even more elusive than dark matter: dark energy. This dark energy appears to be a property of space itself, a kind of anti-gravitational pressure that drives galaxies apart on the largest scales. Dark energy now seems to account for the majority of the universe. About 68% of the cosmos is this mysterious dark energy, which leaves about 27% as dark matter and just 5% as normal matter. In essence, empty space isn't truly empty. It's imbued with this energy that causes space to expand. The concept isn't entirely new. Decades earlier, Albert Einstein had introduced a term called the cosmological constant in his equations as a sort of repulsive force to counteract gravity, though he later abandoned it. Now, that idea has returned in force. Dark energy could very well be Einstein's cosmological constant made real, or it might be something else entirely, perhaps a new field or fluid that permeates space. Whatever it is, we know it's there from the way it shapes the universe's fate, even if we can't see it or bottle it. And unlike dark matter, which clumps around galaxies, dark energy seems to be uniform and smooth, affecting all of space on large scales. The realization that we live in a universe dominated by dark matter and dark energy is a humbling one. We, with our telescopes and instruments, only directly perceive a tiny sliver of what is out there. All the glowing stars and galaxies are like foam on a vast, dark ocean. By decoding subtle signals, we have become aware of the ocean itself, yet we still yearn to understand its nature. Perhaps future discoveries will shed light on these dark components and reveal how they fit into the cosmic story. For now, dark matter and dark energy are central characters in that story. Dark matter's gravity pulls galaxies into clusters and holds those galaxies together, while dark energy drives the overall expansion of the universe ever faster. Their struggle, gravity versus expansion, will determine how the cosmos evolves from here. Will gravity someday rein in the expansion, or will dark energy win out and send galaxies rushing apart at an ever-increasing pace? The answer will decide the ultimate fate of the universe. To explore that fate, we must venture beyond the present into the realm of the far future, peering ahead to see what destiny awaits the cosmos in the end. In light of what we know now, the universe seems destined for a long, dim future. With dark energy driving an ever faster expansion, a dramatic cosmic finale like a Big Crunch collapse has become highly unlikely. Instead, the most widely accepted fate is an endless spreading out, a scenario often called the Big Freeze or heat death. In this vision of the far future, the cosmos goes on expanding forever, growing colder and more dilute as eons pass. What would a big freeze look like? Trillions of years from now, any being still around would see a very different night sky. Over immense timescales, distant galaxies will slip beyond the horizon of visibility, accelerated away by dark energy until their light can no longer reach us. Our Milky Way, long before then, will have merged with its neighbor galaxies in our local group, forming one great island of stars adrift in an almost empty void. As time marches on, new stars will stop being born because the raw materials, the gas clouds, will be used up or too dispersed. The existing stars, one by one, will burn out. First the bright massive stars, then more modest stars like our Sun, and finally even the long-lived red dwarfs will exhaust their fuel. The universe will gradually lose its starlight. After about 100 trillion years or so, an almost unthinkable span, star formation will cease entirely. The stellar era that we currently enjoy, with its glittering galaxies full of billions of stars, will be over. The cosmos will enter an era of degeneration. All that remains will be the remnants of stars, dim white dwarfs, neutron stars, and black holes, plus diffuse gas and dust slowly thinning out. Gravity might occasionally cause some of these remnants to merge or collide, creating a brief flicker of activity, but on the whole, the universe will grow quieter and darker. Over quadrillions and quintillions of years, even those faint embers will transform. White dwarfs will cool to black dwarfs, essentially frozen cinders of stars. Collisions might send some objects into black holes, or fling them out of galaxies entirely. Galaxies themselves will disperse as their remaining stars escape or fall into central black holes. In time, black holes will dominate what's left of organized matter, each one slowly swallowing any stray particles that wander too close. But even black holes don't last forever. They very slowly evaporate by radiating away energy, a process predicted by Stephen Hawking. For a black hole as massive as the Sun, this evaporation would take unimaginable timescales, 10 million trillion years or more. For the supermassive black holes weighing billions of suns, it would take vastly longer, on the order of a Google years, a 1 followed by 100 zeros. Yet given enough time, even the giants will eventually vanish, fizzing away into faint Hawking radiation until nothing remains of them. When the last black hole has evaporated, the universe will have reached a final, profoundly simple state. No stars shine, no planets warm. The particles that are left, electrons, positrons, faint photons and neutrinos, are thinly and evenly spread across a volume of space that is effectively infinite. All energy differences will even out, and the cosmos will settle near a temperature of absolute zero, the coldest possible. In this silent expanse, no organized motion or life is possible. This is the ultimate heat death, a universe that has run down and expended all its free energy, doomed to eternal stillness. There are other, more unsettling possibilities, though they remain speculative. One is the Big Rip scenario. If dark energy isn't constant, but grows stronger over time, if its repulsive effect were to increase, the expansion of the universe might accelerate to the point that it overcomes all forces binding structures together. Billions of years from now, perhaps 20 or 30 billion years in the future, according to some models, dark energy could become so dominant that first galaxy clusters, then galaxies, then solar systems can no longer hold themselves together. Everything would be stretched apart. Eventually, even the atoms that make up matter might be torn asunder in the final moments. In the very last fraction of a second before the end, every molecule, every atom, and even the fabric of space-time itself could be ripped to pieces. The universe would end in a catastrophic dissolution of all structure, a true Big Rip. Current observations suggest this extreme will likely be avoided. Dark energy appears consistent with a constant force, the cosmological constant. But until we know for sure, the Big Rip remains a theoretical possibility. Long before modern science, people imagined cosmic renewals or final apocalypses, worlds ending in fire or flood, or being reborn in cycles. For a time, some scientists similarly thought the universe might oscillate, collapsing in a big crunch and then exploding in a new Big Bang, over and over without end. But the discovery of accelerated expansion has all but ruled out an eternal rebound under the physics we know. Unless dark energy somehow miraculously fades away or reverses, for which we have no evidence, a global Big Crunch collapse will not occur. Instead of a dramatic fireball ending, the universe's story likely concludes in a slow, quiet fade-out. The Big Freeze offers no grand fireworks or second act, just an ever sparser, ever colder, ever darker cosmos stretching toward eternity. In a sense, it's not a sudden death at all, but a gentle dimming of the lights over an infinite expanse of time. It is the universe growing old and falling asleep. All of this, of course, takes place on timescales so far beyond human experience that the numbers lose meaning. The death of the last star, the fading of the last black hole. These happenings are so distant in the future that our mind struggles to grasp it. We are talking about ages of time that make the current age of the universe, nearly 14 billion years, seem like a brief flash by comparison. By the time the cosmos truly approaches heat death, not only will Earth be gone, but likely so will any conceivable descendants of humanity, and even the memory of our galaxy itself. These are events in a universe with no eyes to see and no minds to witness, a universe long past the era of stars and life. It's a realm of time and existence utterly foreign to our everyday sense of a long time. And yet, paradoxically, we can predict it. Here, from our little window in time, we have projected the story forward as best we can. Knowing the likely fate of the cosmos can cast the present moment in a new and profound light. It reminds us that the age we live in, with bright stars, rich galaxies, and living planets, is special. This is the age of light and life, and it will not last forever. Far in the future, the universe may be emptier and darker, with no eyes to appreciate it. But right now, we do have eyes to see. We have minds to wonder. In the face of the cosmic timeline, our human life is incredibly brief. But that brevity lends each moment a certain sweetness. We find ourselves alive at a time when the universe is vibrant and young, full of stars and possibilities. We are witnessing the cosmos in its splendid spring and summer, long before the inevitable winter. That realization can inspire a deep gratitude for simply being, for having the privilege to experience this universe. Whatever the ultimate fate of the cosmos, endless expansion in darkness, or a final catastrophic rip, it lies so far beyond our human horizon that it need not frighten us. Instead, it can humble us and perhaps comfort us. It shows that even the stars and galaxies have a life cycle. Nothing is exempt from change. And yet, here we are, tiny, but endowed with the ability to understand these grand processes. It is remarkable that we can even contemplate the end of the universe. We who occupy but a speck of space and a blink of time have been able to reach out with thought and observation to grasp something of the universe's entire arc from birth to death. This knowledge is a tribute to our curiosity and intelligence. It's a triumph of the human spirit, and it naturally leads us to reflect on ourselves and our place in the cosmos. Since the dawn of our species, we have looked to the heavens for answers and inspiration. Our distant ancestors, gathering around fires under the open sky, wove stories into the patterns of the stars. They saw heroes and monsters, gods and animals shining above, connecting their lives to something grand and eternal. Every culture found its own myths among the constellations, yet all shared the same fundamental wonder at the night sky. We today gaze up at essentially the same stars that twinkled over ancient Mesopotamia, over the pyramids of Egypt, over the first cities of China and the plains of Africa. The sky is a universal heritage, uniting everyone who has ever lived under it. No matter who or when or where, we all inhabit the same cosmic backdrop. Over time, our understanding of that starry canvas has deepened immeasurably. We learned that those pinpoints of light are distant suns, that the Earth is not the center of all things, but one world, orbiting one star among billions. We discovered that the Milky Way is just one galaxy among countless others, and that the universe is far older and larger than our ancestors ever imagined. Through the work of curious minds, from Galileo peering through his telescope, to Newton, to Einstein, to the scientists of our own time, we gradually found our true place in the cosmos. This journey of understanding has been a triumph of human spirit and intellect. It has made the universe feel at once more comprehensible and more awe-inspiring than ever. Yet even as science has given us answers, the sense of wonder has only deepened. Knowing the stars are fiery suns trillions of miles away does not diminish their beauty. If anything, it enhances it. When we look at the Milky Way arching overhead on a clear night, we can appreciate it not just as a hazy band of light, but as the collected glow of billions of distant suns. We understand that that misty band is the disk of our galaxy seen from within, and that beyond it lie innumerable other galaxies, each with its own stars and worlds. The sheer scale and majesty of it all can be overwhelming, yet oddly comforting. It reminds us that we are part of a vast and ancient cosmos, one that has given rise to galaxies and stars, and, on at least one small world, to living beings capable of contemplation. The more we learn, the more profound and elegant the universe appears, and the deeper our reverence grows. This cosmic perspective can be deeply humbling, but it is also profoundly enriching. We have learned that we are made of the same material as the stars, the iron in our blood, the calcium in our bones, the oxygen we breathe. All were forged in stellar furnaces and supernova blasts long before the Earth formed. In a very literal way, we are children of the stars. It is a realization that bridges the gap between the human and the cosmic. As we often say, we are stardust that can think. The universe birthed conscious beings who can admire and study the universe. We are a means for the cosmos to know itself. That thought can give a sense of purpose. By living and thinking and exploring, we bring the universe to life. We are tiny, yes, but our minds encompass galaxies and eons. We should feel neither insignificant nor arrogant, but grateful. out of cosmic events, billions of years past, on a small planet around an ordinary star, consciousness bloomed. And here we are. The stars have watched over humanity for as long as we've existed. Generation after generation, under the same sky, people have lived out their dramas, their triumphs and tragedies, with the silent stars above as witness. Think of it. Every ancestor you have ever had looked up at this very sky. They might have had different interpretations, perhaps believing the sky was a solid dome, or that the stars were campfires of the gods, but they felt the same awe. The view has changed little. The constellations shift slowly over thousands of years, but remain recognizably the same. When we look up, we share an experience with all who came before. In a world so often divided by borders, cultures, and time, the sky is one thing we all have in common. It links us across continents and across centuries. From the vantage of space, we've seen how delicate and small our Earth is. The famous pale blue dot photograph shows our planet as a tiny speck of light in a vast darkness, just a pixel suspended in a sunbeam. All of human history happened on that mote of dust. This perspective is sobering and enlightening. It underscores the folly of human arrogance and hatred. On that tiny dot, every war was fought, every human love story unfolded, every invention conceived. It should inspire us to treat each other kindly, for we are all passengers on the same small ship, all part of a fragile family in the cosmic ocean. The cosmic perspective doesn't belittle human life, it elevates it by showing how precious and unique our planet is. There is nowhere else, at least in the foreseeable future, for us to live. Earth is our cradle and our home, and it deserves our care and reverence. The realization that the universe will not intervene to save us from ourselves, that it's up to us to create meaning and safety here, can be a unifying and maturing realization for our species. Standing under a starry sky often brings a sense of peace that is hard to find elsewhere. There is something about the calm eternal night that puts our minds and hearts at ease. The stars do not judge us or demand anything of us. They simply shine. When we feel lost or overwhelmed, a glance at the night sky can remind us that we are part of a much bigger story. The troubles of the day start to shrink just a little when measured against the backdrop of the cosmos. Many people have felt lonely or troubled, then looked up at the stars and felt comforted in knowing that the same stars shine on loved ones far away, or that the beauty above is constant and enduring. The night sky connects us not only to each other across distances, but also to our own inner sense of wonder. It can be like a gentle hand on our shoulder, saying, "Take heart. You are part of something vast and beautiful, and you are not alone under these stars." Our journey through space and time, though conducted mostly with telescopes, mathematics, and imagination, has been one of the greatest adventures humanity has embarked upon. We have sent robotic emissaries to planets and moons, and even beyond the boundary of our solar system. We've listened for whispers of the Big Bang and mapped the afterglow of creation. We've detected gravitational waves from colliding black holes across the universe. We have, in essence, become explorers, not just of lands and oceans on Earth, but of the cosmos itself. And we are still at the very beginning. There remain deep mysteries. What exactly is dark matter? What is the true nature of dark energy? Are we alone in the universe, or is life a common thread woven through many worlds? Each mystery we solve leads to new questions, ensuring that the cosmic journey of discovery will continue for future generations. We are fortunate to live in an era when so many cosmic truths have been unveiled, yet so many remain to tease our curiosity. As we come to the end of our long cosmic journey in this narration, we find ourselves back where we started, under the same marvelous sky, filled with wonder. We have traveled from the birth of time, through black holes and invisible matter, all the way to the universe's future death, and finally returned to the present moment, this fragile oasis of life rotating gently beneath the stars. It's a good time to reflect on what all this means for us. Perhaps it gives us a profound sense of gratitude for existence, for knowledge, for the chance to be awake in a universe so endlessly interesting. Perhaps it instills a quiet humility, recognizing that, as special as we are to ourselves, we are part of something much larger and older, and that our lives are chapters in a greater story. Perhaps above all, it leaves us with awe, simple, childlike awe at the fact that anything exists at all, and that we get to witness it. Whenever you need to, you can step outside on a clear night and look up. The stars will be there, waiting. The same stars that guided our ancestors home, that fueled our myths and our sciences, that silently regard us all. Let their light wash over you. Think of how far it has travelled. Years, centuries, millennia, across space to reach your eyes. In that moment, you are connected to the vastness of time and space, yet firmly grounded on your own piece of earth. There is something quietly reassuring in that balance. The universe is immense beyond measure, and we are small, but we are here. We belong in this universe. We sprung from it, and we are witnesses to its wonder. Our marvelous cosmos has dazzled us with facts and mysteries, but it has also touched our hearts. It reminds us to cherish our pale blue dot, to treasure each other, and to remain curious and open to the unknown. In the end, the greatest lesson of the cosmos may be the value of unity and perspective, understanding that we are one tiny part of a vast whole, and that our true significance lies not in how much of the universe we control, which is none, but in how deeply we appreciate and love the universe and each other. As this journey comes to a gentle close, we find ourselves under the same stars that have always been there. They shine as they did long before we existed, and they will shine long after we are gone. In that steady, patient glow, there is a kind of promise. The promise that knowledge and wonder will continue, that new eyes will lift to the sky and ask why and how, and that the story of the cosmos will go on, with new chapters we can scarcely imagine. We, here and now, have been part of that story, thinking about it, learning about it, and finding meaning in it. Take a moment to feel the calm of this cosmic perspective. The universe is vast and old, and our lives are short and precious. Yet, against all odds, here we are, conscious and full of wonder, able to admire the cosmic tapestry spread above. It's a privilege beyond measure. So, beneath the endless sky, let's embrace the sense of peace that knowledge and awe can bring. Let us gently close our eyes, knowing that when we open them again, the stars will still be there, watching over us as they always have. We are home in this universe, under the same stars, together. And in that thought, there is a deep and lasting tranquility.